So this is a great opportunity to have real conversations and have real live sessions of building AI. So yeah, that's something new for us nowadays. And unfortunately, so yeah, I'm really glad to have all of you here in Cetinje and to attend all of these sessions. I will not spend too much time for you. So I've been basically in charge of making to-do lists for the past half year. It was yeah, a really hard job for me because I'm really bad at multitasking and organizing. So yeah, if anything goes wrong with this call, yeah, you can blame me. I hope you can find me in this picture. I'm Nicola, and yeah, feel free to talk with me anytime during these days. I'll just I'll just emphasize once again, this is not just a school. Yeah, this is a great milestone for us at Maya, at Montenegrin AI Society, because we started as an organization 3 years ago, and now we have the best and the greatest AI conference here in Montenegro ever. So it's a really big milestone for us, and yeah. Here I will just introduce Milutin as well because he's not present now with us. He will come in a few hours. He's our CEO, and yeah, he told me that I'll just tell it as he told me how to present him. So yeah, at 22, he tried to stop being a computer scientist and pursue a career as a comic book author and an early internet comedy creator, and he's very good at it. So
that helped.
These photos and the designs behind these schools, he's in charge of it and he created all of this content. So yeah, that's him. You will have a chance to meet him. He's, I think, the tallest of us and it's easy to spot him. I'll just give floor to each of our members because this is an amazing team and it would be impossible to make all of this without them.
So good morning. Nice seeing you all. Welcome to Montenegro. We are so happy to have you here. As you learned by buying tickets and finding way to Montenegro, we are a really small country, and this is a very big and important event for us. I am an engineer by training, a researcher by chance. I'm, as you may predict, because of me being here, also passionate about AI and data science. If you need some questions about issues we have in organization, feel free to come. I'm happy to chat and try to help.
Good morning, everyone. From my side, I'm Stevan Čakić. I'm coming from University from Montenegro here, from University of Donja Gorica. So I was responsible, and I'm still responsible for volunteers for my students. And I really like to work in education. This is my love, working with students, with young talents. My research area is related to computer vision. Recently, 6 months or 5 months ago, I finished my PhD here. So that's a short story about me.
Good morning, everyone. My name is Milo. I'm also from Montenegro. Right now, I'm working and living in Poland. In terms of my tasks, I tried working on like miscellaneous ones, but the most prominent one was transportation that I worked together with Alexander. Hope everybody got here. One that didn't go so well was the internet provider. I tried my best, but we all saw how that went down. Apart from that, I'm a lead AI engineer at EEML Systems. And before that, I was working on machine learning in computer vision for MedTech and a bit in the banking domain. That's all.
Yeah, so good morning, everyone, also from my side. And I wish you a pleasant stay in Montenegro, and I hope everything will go well. I won't speak too much, as in a few days I will be again here on the stage and present a little bit about my research. But my name is Alexander. I am, for you, because we have two Alexanders, I'm usually Plameni or something like that. And this is Aco, or Alex. So as Stevan mentioned, me and him are in charge of volunteers. So part of all volunteers come from University of Donja Gorica. Part of volunteers come from University of Montenegro. And I also like working with young talents, young students. And I wish you a really nice school. Yeah, see you soon.
Hello, everyone. So my name is Alexander. You know as me a transportation leader here in the Montenegro for the EEML. And tomorrow we'll close everything for the transportation, and Sunday will be the end day for transport for the airport and end of school. So I'm working as a data and AI governance lead at Erste Bank in Podgorica. And in free time, I'm organize a shuttle buses for everyone and everywhere in the Montenegro as well. So.
Hello, everyone. My name is Zdravko. I came from Podgorica. My journey with data started 10 years ago when I was led the largest loyalty program in Montenegro. Then I moved to Croatia to work in one of the largest retail chain, to work as a data scientist to optimize retail processes, currently building AI agents, and that's it. I'm here in charge of a little bit of poster, a little bit of food, and that's it. Thank you.
Good morning, everyone. My name is Tamara. I think we met yesterday, so I hope you remember me by voice, if not by face. I'm here representing MAIA, Montenegrin AI Association, but also one of our sponsors, which is Coinis, which is a local company where I work. So I'm a senior data engineer here at Coinis, and I also went to University of Donja Gorica, where I finished my master thesis in artificial intelligence. But I'm very passionate about this event, and I'm so lucky. We are all so lucky to have you here in Cetinje. We are happy, and we are hoping that you're enjoying. So if you have any troubles with accommodation or anything about your rooms, I'm the person you should contact. But please be gentle, because I have a huge smile, and we will figure everything out. No worries. Thank you.
Hello, guys. Last night was like, oh.
Matko is over there.
We used to say in Montenegro that who has rakia for dinner will have water for breakfast. So I hope that everyone is well hydrated this morning. Good morning. My name is Jovan Jablan, and I come from Montenegrin AI Association. I'm from Cetinje, and it is a great honor to have all you here, well-educated young people. So I hope that you will enjoy whatever you need. We are here for you. And a little bit about myself. I'm a teaching assistant at University of Donja Gorica. I'm also a PhD researcher in Budapest in field of how AI impact on human rights. I'm a lawyer, actually, so my task is to talk with you in terms how to create responsible AI systems. So once again, thank you very much. Enjoy whatever you need, just reach us. Thank you.
Good morning, everyone. I'm Itana. I currently live in Warsaw, Poland, and work there as a senior machine learning engineer at Schneider Electric. Previously, my main specialty is in computer vision and was for the past 5 years, and I was working in the field of climate change, geospatial data, until I kind of sold my soul to finance. So now I'm working in the domain of time series forecasting. In this whole team, I was mostly looking at the budget. So yeah, checking if all the numbers are okay. So yes, I really am so happy that you are all here, and my passion is that because I've been outside for the past 10 years, living abroad, and I always come to Montenegro for basically holidays and vacations and try to do something with this amazing team and organize cool events like this, just to give a bit of a contribution to our AI ecosystem. Thank you.
Good morning, everyone. I am Danilo Planinic. I'm teaching assistant and PhD student at the University of Montenegro. My research interests include graph neural networks and the possibility of their application in different areas, especially energy sector. Mainly, I was in charge of organizing gala dinner and field trip on Thursday. I am sure that we will all great fun. I am sure that the music, I hope that the music would be interesting to everyone. As a teaching assistant, I'm happy to have and to be able for all of us to attend those great lectures and the tutorials during this school. And I hope that you are having fun in Cetinje. Thank you.
Okay, as you can see, we have a lot of great people here in Montenegro wanting to join these global AI trends that are nowadays really increasing and are very important in the world. So we are really looking forward to talk with you, to have friends with you, and to enjoy all of these days in Montenegro. We'll have really good weather, so I hope you're as well enjoying. I see a lot of people running in the morning and hiking and doing a lot of stuff. So Montenegro is great for this. And yeah, we are really glad that have this school in this mountain place and enjoying this mountain place in nature alongside the AI. So yeah, once again, welcome. And I hope you will enjoy today's sessions. Thank you.
We'll need just a few minutes to set up. It's okay. Okay. Cool.
Here's the mic. Do you need to present it? Oh, it should be. Cool. Okay.
I think we're ready to get started with the first lecture of the day. So it's my great pleasure to introduce Andrea. She did her undergrads and masters at Cambridge, where she got the best thesis award in her year. And then after that, she followed with a PhD at Mila, where she worked on various topics, mostly around graph neural networks and drug discovery, but also reinforcement learning. And she had a NeurIPS 2021 spotlight on algorithmic reasoning, and she did a bunch of internships while there, among which also DeepMind, where if I remember correctly, is the place where I've met Andrea properly, and we got to talk a lot more. And after her PhD, she went to Isomorphic, where she continued her work on drug discovery, which led to publications in journals like Nature. Yeah, and with that, it's a great pleasure to introduce Andrea, and I'm curious to see her talk on reinforcement learning. Thank you.
Okay, now? Yeah, okay. So I have a live demo, which is why I was taking a extra minute. I'm gonna try to see if it works. It counts on the Wi-Fi working in a particular way. If it doesn't, then I'm gonna switch to an offline version, but let's see, let's give it a try. So yeah, I'm gonna talk about RL today. This is actually my third time at EML. 2 years ago, I was, I was giving a tutorial on RL, and then 4 years before that, I was giving like a poster presentation virtually, as it was COVID. As Rosman said, I work at Isomorphic Labs, where I'm interested in finding out what small molecules do and how we can turn them into drugs. And before that, I was in Canada doing my PhD and everything that Rosman just said. But and I wasn't going to say this, but before all this, like my undergrad and everything, I was in Romania. And I was going to math camps in a hotel that looked very much like this. So I got a lot of flashbacks this morning. So my nerves might partially be because of that. Okay, so let's talk a bit about RL. So in a way, we're all using RL in ways that we might know or might not know about. So the most common, am I too loud? The most common and the highest revenue RL is the one in Bandits, which is used for recommender systems. So when you're on Spotify, you want to listen to some songs, sometimes it uses like some feedback that you said, like, I like this playlist or I didn't like this playlist to recommend another playlist for you to listen to. And the same for Amazon, like it can recommend like another product for you to buy, or I think like, what's the other one? So Yahoo uses it to recommend other news for you to look at, and so on. So this is like the one that's like not very popular, but it's like the one that brings a lot of money in. One that maybe a lot of you have heard about, AlphaZero. So this was like a big breakthrough because there was one agent that managed to ace 3 different games, and even beyond that, it managed to really ace Go. So there were like some famous games you might have heard about where the agent found a move that nobody expected. And one that I like is the fusion. So this is like using RL for, I guess, figuring out energy sources. So in this case, RL is used to stabilize and shape superheated fusion fuel. And we're actually going to talk about a very similar agent to what they use there. And one that maybe sort of gave RL a new face in a way, a new perspective, is the RL in LLMs. So RL from human feedback, or the more recent variants, they are all like in most LLMs nowadays. So 1 billion people are using them weekly. Yeah, so what is RL? I keep mentioning RL, but what is it? So we have a bit of a perspective shift from supervised learning, where we're thinking in terms of agent environment loop. At every time we perceive the state, we choose an action, And based on that, we receive a numerical reward. So this is like how the agent interacts with the environment. After it decides an action, the environment feeds it back what is the new state and what is the reward it's receiving based on the state it was in and the action it took. And we're going to talk more about it, but overall, we want to figure out a behavior, so a policy, that maximizes the long-term expected return. So maximizes basically all the points the agent can get, all the rewards it can gather over time. And if you're more familiar with supervised learning, we're just going to do like a small side-by-side comparison. So the learner is not told what actions to take. It needs to find this out through trial and error. And so this sort of changes everything about how we gather data and how we use data. So data in supervised learning is a set of pairs of X and Y's. In RL is self-induced. So basically the RL agent is gathering data while it's stepping through the environment. And then the signal in supervised learning is the correct label. So that Y that we already know is what corresponds to the X. While in RL, it's a reward that in a lot of the cases, it's designed by a human. So it's not like there's no sense of correctness. It's just that it fits the purpose we want. And then in supervised learning, the feedback is immediate. So one loss, for example, you do your gradient descent on that. While in RL, the feedback might come a few steps later. So sometimes maybe the RL will step a few times before getting any signal over whether what it's doing is good or not. And generally, the learning for supervised learning is to learn a map from X to Y. So what is the function that for any input takes us to the correct output? While for RL is to figure out a way to act in a way that maximizes long-term return. Okay, so this is the part that I am not super confident about. If you could, nobody get angry if it doesn't work. I have an offline version. So if you could try, this will only work if you're on the local Wi-Fi, because I'm on the local Wi-Fi, I hope, yes. So this hopefully should take you to a bunch of buttons that are not activated saying yes or no. Well, 2 buttons. If it loads. I'm going to tell you what it's supposed, while we're waiting for it to load, I'm going to tell you what it's supposed to be doing, if it works. So basically, I'm hoping that we will all together train a bandit during this presentation. And this bandit is meant to learn what a nice presentation looks like according to the room. So basically, you're going to have like yes and no buttons, which are going to show up every few slides. And then if you like the slide, you would press yes. And if you don't like the slide, you would press no. And then based on these votes, the RL agent will learn what a good slide looks like and what it doesn't. So did it load? Yes, no, no. Okay. That is sad. Let me see if I can show you a different one. One where we're gonna okay, I'm gonna keep going, I think. Just give me 2 minutes. I have hope that at least the offline one would work so that we can see some fun slides. Okay, let's keep going. I'm a bit sad about it, but I'll share a video afterwards with how it was supposed to look like. So hopefully not much is lost. Okay, so let's set up the problem. Okay, so what are we trying to solve really? What is the problem of RL? So the problem of RL is defined in terms of Markov decision processes. The 5 things you have to specify, so are the states S, a set S, actions, a set A transition function which takes you from a state given an action to a new state, and the reward function which when you're in a state and you take an action, you receive a reward. So that's like the feedback. And the discount factor, which we're going to talk more about in a second. And then the Markov decision processes have this property that is like standard, and a lot of the assumptions count on it, that it's a memoryless system. So the future states depend only on the current state. In practice, a lot of the RL agents stack a bunch of states together to sort of go around the fact that it's supposed to be memoryless. So they sort of like build a memory by gluing states together. But this is like something that we find empirically. And what we want to do is we want to find a policy of how the agent acts. So what is the behavior that is going to lead to the most return? And then when using this policy, it's going to step through the environment, and it's going to have like starting from A0, it's going to take an action, going to get a reward, and going to end up in a new state S1. And going to keep doing this. And what we call this set of data, we're going to call it like trajectories. So this is like the agent rolling through the environment. And what we care about is the return. So what is the trajectory score? Then like overall, how do we add up these rewards that we're getting through time? And the fact that I'm saying through time is quite important because depending on on the value of gamma, it might matter more whether the rewards we're getting are big short term or whether they're big long term. And we're going to see in a second how that influences things. So policy gives one-step decisions, but in general, we have a long-term goal. So we want to maximize over the whole trajectory. So let's have an example. Yeah, in this simple grid world, we have like this winning state where if you reach, you're getting $100. And then you have these 2 death states where like terminal states, where if you end up, your episode ends and you get a penalty of minus 100. You also have a banana on the way where if you step on it, you're going to get -1, and some coins in the corner where you get +1. So you can see that in order to reach to the good terminal state, you have multiple paths you can take. So the blue one steps through the banana. It's going to have overall, assuming that we just add rewards like simply, we're going to have overall return of 99. And then the yellow one, which goes through the coin, is the yellow is going to have 101. And the pink one is going to have 100, which just goes straight through it, doesn't go through the banana or the coin. And this is where the discount factor becomes relevant. So I was saying that the reward gets scaled by the discount factor. The more you step, the further in time you get, the more the discount factor gets powered up. So the discount factor scales every future reward. And looping through this S14, so the coins, theoretically, if we didn't have a discount factor, if we just added things normally, would sum up to infinity. But the discount factor is what stops us from doing this sort of thing. So what do different values of gamma mean? If you think a bit about it, like what would maximize like the short-term gain? What value of gamma? Let me show you again the return. What value of gamma would maximize the short-term return? The map, yeah. Okay, I'm going to give you 2 options. Who thinks the gamma 0 is going to maximize the short-term return? The other option is going to be who thinks gamma 1 is going to maximize short-term return? 0 and 1. Okay, so if we think 1, basically it means we sort of ignore gamma, and it's gonna keep adding them. So then it's gonna add. So then it doesn't optimize short-term midterm, it optimizes long-term midterm. Well, if we have 0, basically only the first term stays. Everything else is gonna be multiplied by 0, and it's gonna disappear. So 0 is the shortest term we could think about. It's literally 1 step. Okay, and this is why basically we're in this sort of environment, we're not gonna just infinitely step through like something that looks good, because in reality, like we shouldn't gather just one coin at a time. Okay, so now that we know a bit about how the MDP looks like, so we have state, actions, transition function, reward, and gamma, we're gonna think like what are we trying to achieve in this problem? For an MDP, we have to find a way to choose actions, so figure out what is the behavior, which maximizes the agent's long-term expected return. So this is how we define, we say J is the way we think of like expected return, and we're gonna optimize the theta parameters that lead us to having the trajectories that lead to the most return we could gather. And we're gonna do this in RL environments. So we already saw the grid world, which is like the tabular environment, the simplest ones, the ones where we can prove a lot of things and we can like exhaustively solve things. And then we have more and more complicated environments as we progress in algorithms and the power of agents. So card poll is one which is like, we basically have to balance a poll to stay up. If we don't do, the actions are like just up, left, right, and we'll have to like keep it up. And then there's Mujoko, where there's like all sorts of skeletons that are trying to do actions. So for example, in this case, is the humanoid trying to walk. This is already like quite a good agent. It's sort of working. And there are like some recent, well, not that recent anymore, I guess, like the last couple of years, where we can, thanks to LLM progress, we can actually generate quite impressive words where the agents can see things more realistically, and it doesn't require us like to like hard code every single frame and every single action. Okay, so now that we talked about what the problem is and where we're trying to solve it, I'm gonna give you the simplest example. So these bandits that I mentioned that give the highest revenue in RL, we're gonna strip the problem to just one state. So the bandits are called bandits because they were associated with slot machines, and they were bandits in stealing people's money because they always are like not favoring the humans playing them. So the idea is that you pull an arm, you get a noisy reward, and you repeat. And if you have multi-arm bandits, so you can think of it as multiple slot machines, you're trying to figure out what is the slot machine that's gonna give me the highest reward, the highest return. So basically, I'm gonna try to pull each of them until I figure out, oh, this one gave me actually something positive. And if it was me, I would then go back and I would try the positive one again. Or maybe I was like, oh, maybe this is not the best one. Maybe I was just unlucky. Maybe I will go and try one of the other ones. So this is the trade-off that you're gonna hear a lot about in RL, the exploration exploitation. So exploration is when you're not sure that you're doing the right thing, you're gonna go explore some new options. And exploitation is when you figured out something good and you're gonna keep harvesting it. And in a way, like another example from my day-to-day, when I go to a new place, I have an option of going for like my familiar option, the pizza. So I'm gonna just exploit what I already know. There's not much you can go wrong with pizza. Or I might exploit a new place and I'm gonna try Plieska pizza. Well, I've tried it a bit. It's not that new to me anymore. So that's like, you can swap it for your example of something new. Okay, and the way, like one strategy, for example, is you can act greedily. So once you know what you like and what's the slot machine with the best reward, you're gonna take the best action. So that's greedy behavior. But in epsilon greedy, we're gonna slip in a random action epsilon from time to time. This is actually a very simple strategy, but it's actually quite hard to beat. And we're gonna find it in different forms and shapes throughout agents in this presentation. And this is what we're supposed to see in the demo that is not working. So basically the slides were supposed to change colors and layout. Should I try it one more time? No, I'm not. Okay. And then the idea was that you would get a plus and a minus, like a yes or a no if you like it or not. And then the bandit would figure out which of these configurations you liked more or less. And I was really hoping you're not gonna choose purple, because then the whole presentation looks purple. And believe me, I went through it. It's interesting to see for 60 slides. Okay, so I will share with you afterwards what the bandit would have done. But in the meantime, let's talk about mushier stuff. So when we have more than one state, we're gonna have to learn a policy, and we have to formalize some things. So one way to learn a policy is to directly optimize the policy itself. So this is using policy gradient methods. And the idea is that if we parameterize the policy, we can think of it as like any neural network. We can do gradient ascent on the policy. So what does this mean? Let's recap. The objective is to find the policy that maximizes the expected return. And then, so this is the J of theta, where the theta is the parameters that are parameterizing the policy. And then we're gonna take like the steps that are leading us to like the direction of more return. So we're doing gradient descent on the return basically. So this should look quite familiar. It's like what we do in supervised learning, but it's sort of like flipped because we're going for the gradient ascent version. And I'm gonna tell you a bit about what are some tricks that we need to get. So if you're familiar with RL, like maybe this is gonna be, like, depending on how familiar you are with RL, this might be a bit interesting to you. So theta is in the distribution, but it's not in the return. So basically, if we sample a return, backpropping through G, so like through one return, is gonna give us 0 because it's not parameterized. And the other thing is we can't really enumerate all trajectories for any meaningful environment. So we're gonna have to do a trick. We're gonna use the log derivative trick. So if we can compute the policies on gradients, then we can compute the gradients of J, which is what we care about. Basically, we're gonna do this thing where we multiply it and divide by the trajectory's probability. And the overall gradient over the expectation is gonna turn into an expectation over the log probability. Expectations over the derivative over the log probability. And then basically going back to what our J was, so swapping back this F for our J, this is equivalent to having an expectation over the gradient of the log probability of the policy scaled by the return. So this is where things get interesting, because here you're noticing we're scaling by the whole return. So there's no way of differentiating what was a good action, what was a bad action. We're sort of clumping up all the actions the agent took in the trajectory, and we're computing one return, and we're scaling the whole gradient by it. We're gonna come back to that, but let's formalize. Let's formalize what this means. So basically, we're starting with random parameters, theta, so a neural network, the classic way. We're gonna step in the environment. We're gonna gather this trajectory. So we're in state 0, we're taking an action A0, we're getting a reward. And we keep doing this until we end up in a terminal state or the environment times out. There are environments that are set to time out. The way we do this is at each time we sample the action from the policy that is parameterized by theta, by the neural network. And the rewards and the transition function, like the next state, are given by the environment. So then when we reach the end, we're gonna compute what is the return of this trajectory. So how much reward did I gather? And as we were seeing, we're gonna use the gradient ascent to sort of nudge the parameters in the direction of the return, of the highest return. So if the return was positive, then the parameters are gonna get a sort of a bump in the direction. If the return is negative, then it's gonna go backwards. It's gonna say, well, this was not a good decision. But as I was saying, this sort of scales the parameters by everything, like everything that was happening is summed into one number. So it doesn't really have credit assignment. It can't really say, this action was good, this action was bad. It's all about what it ends up in the end. And in one of the environments that I was playing in, basically in a trajectory that was good, a lot, like half of the actions almost were bad. So you can think of it as like the banana thing. You could go through the banana, which is a bad action. You're going -1, but if you end up in the terminal state that is good, you're overall saying, well, this was a successful episode. But we should discriminate between good actions and bad actions. So, for example, if we get a higher reward, could we know if a better action existed? And if we get a penalty, but no better action existed, then maybe that wasn't a really a bad action. And the way we're gonna learn about this is through value functions. So value functions help us distinguish as an action and figure out like if it's better than expected or worse than expected. In order to do this, we need to know what we expect and how to estimate it from experience. So the environment is not telling this as this. Okay, so these value functions, what are they? Basically, the value of a state is the expected return from that state S under a certain policy. So here, I'm back to my grid world, and I'm gonna say I have a random policy. So with equal probability, I'm gonna go up, down, left, right. And by doing this, basically you can see, well, the final state has the value of 100, and the ones that are nearing have a bit of a higher value than the ones that are far. But in a way, it's not very discriminative. But if we have the optimal policy, so if we really know how to act in the environment, this will give us like very fine-tuned values. We can see, well, if the banana has a value of 95 because you're only just 2 steps away from the good terminal state, if you know how to act from there. Any questions? I feel like maybe I should take a break and let you observe this. If you have any questions, maybe now is a good time. Okay. So how do we compute the values? Like I showed you what some values might look like, but how do we compute them? So the basic idea is that if I am in a state, I can compute the return by saying my overall return will be my reward in my next step, plus whatever return I'll get from there. So in a way, we can think of it as similar to like computing shortest path between 2 places. So going from Podgorica to Kotor, the shortest path, theoretically, goes through Cetinje. That means that if that is the shortest path, then the shortest path between Cetinje and Kotor must also, like, that must be the shortest path. Can't go through some other place. So this gives us like a recursion. We can solve the problem backwards. So going back to what I was saying, if I want to compute my return from this state 0, I can compute the reward from state 1 and the return from state 1 onwards. Does this make sense? Okay. And this is the strategy we apply for computing the value. So the value from state S is the expected value from getting the reward, and also whatever value we'll get from there. Yeah, so we'll go in more depth in a second, but basically this is the backbone. So if you understood this idea, you'll understand the next few slides. They're just like building on this idea. They are the dynamic programming, TD learning, Q learning. They also have the same core idea. And when we're able to compute, so why did we start on this adventure of figuring out what values are? We want to figure out if an action I'm taking or the state I'm in is better than expected. So values are going to help us figure out what is expected and how does my current value compare to the expected value. And then I will be able to use this to sort of do proper credit assignment. So I will be able to distinguish good states from bad states. how do we get? So, okay, I showed you like how do you think about computing return, but how do we compute values? Yeah, so there are three ways to use the Bellman equation. Basically, we're gonna either, so the white dots are states and then the black ones are actions. So we can think of it as, if I'm in a state, I can look at all possible actions I could take, and then look at what the state in the next point will be from all these possible actions. So this is like a sort of exhaustive, and it assumes I can sort of simulate what would happen if I took all possible actions from this state. The temporal difference is like a sampled version of this. So I'm in a state, and I will just look at one action. So basically what my policy would give me, I would just sample one action and look what my value of my next state would be. And the Monte Carlo is the one which goes depth first. So basically I will keep sampling until I reach a terminal point. And then this will give me like one estimate of what my value could be. Okay, so let's go in more depth. So if you know the transition function, so if you know which state you end up in, if you are in a state and you're taking an action, you can sort of sweep the full expectations. So you can sum over all actions and figure out what are the states you're gonna be in and compute all this like reward plus gamma value of the next state. If you can't do this, so if you don't have access to the transition function, if you don't know what your state is gonna be where you reach, then Monte Carlo and temporal difference are sampled proxies. But again, if you don't have this is actually another interesting part of RL where we can learn it. So we can turn a model-free RL agent into a model-based RL agent, and we're gonna talk a bit about it. I don't know if you saw it, but basically it was dispersing. Let's see if it, oh, okay, it's looping again. Basically it's computing the value backwards. So what we were saying about recursion, the shortest path from Cetinje to, the shortest path is from Cetinje to Kotor, so then the shortest path from Podgorica to Kotor must go through Cetinje. And it does the same. Basically, if I have like value 100 in here, then I'm gonna compute what the neighbor's values are. So it's computing it backwards. Yeah? Okay. And I was saying we can only do this if we know the transition function. So if we can actually estimate where we're gonna be from all actions in the current state. And sometimes we don't have this. We don't have access to the transition function, but we can learn it. So instead of learning a policy directly, model-based RL, so some famous ones are Dreamer, mu0. mu0 is like a sort of built on AlphaZero with learning the rules of chess, of Go itself. And this model-based RL is gonna first train neural network to approximate the underlying MDP. So what's it gonna do? It's basically gonna learn if I'm in a state and I take an action, the neural network is gonna predict what will the next state be like. And then same for the reward. If I'm in a state and an action, a neural network is gonna try to predict what is the reward I'm gonna get. And then once I learn these neural networks, in reality, I learn them at the same time as I'm learning to act, I can use them to figure out a better policy. So what are some pros? This is all I'm gonna say about model-based RL. This is like, it's a very interesting part of work, but I think a lot of the recent work is on model-free RL, so we're gonna mostly stay on model-free RL for the rest of the talk. But basically the pros for model-based RL are sample efficiency. So basically if you have a good model of your word, you don't have to really act. You can sort of imagine. So you can use your model of the word, the networks that the model learned, to simulate what would happen. When you simulate what would happen, that means you can also plan. Again, you don't have to act to figure out where would you end up. You can plan, and you can use that plan to figure out better ways to proceed. Other things you can do if you do model-based RL, you can transfer to other tasks in the same environment. So yeah, basically, if I already know if the transition function is not changing, that means I can solve a bunch of problems in the same environment. I already solved half of the problem. And it's also a pro that we can like we can safely do things, because if we can plan, if we can imagine what's gonna happen, then we don't need to take the dangerous action to figure what's gonna happen. The cons are that basically your plan is gonna be only as good as your models. If you have an inaccurate model, the more you step with it, the more the errors are gonna compound. And then sometimes learning the model is as hard as learning a behavior. So figuring out the rules of the environment, the rules of the world is not trivial. And this might require training and inference compute that are quite intensive. So now let's go back to model free RL. So we assume we don't have the transition function and we're not gonna learn it. We're just gonna sample things. So basically in Monte Carlo, we said we're gonna go depth first. I'm gonna keep taking actions until I reach the terminal state. And I'm gonna compute the actual return after time t. And I'm gonna use that to update my value. Any questions?
Hi. So I don't have much of a background in reinforcement learning, but what you've just been talking about reminds me of A-star search. So can you draw parallel a little bit there? Or maybe when we say chess, alpha beta search with pruning?
Yeah, so basically, if we have these models, we can do Monte Carlo tree search, we can do all that stuff that you're talking about. These models enable us to do search together with that. So yeah, I guess, they go hand in hand. Okay.
Oh.
So that was depth first. Now we're gonna talk about something that's even simpler, so temporal difference. Basically, we're just gonna look at one-step updates. So we have like this one step, we're gonna use that. So the reward from the next step. So basically I can update the value by looking at what is my reward from that I get to the next step, plus the value from the next step, minus whatever I already estimated. So this is sort of gives me like a temporal difference that I can add to my value. Okay. So now let's compare the two. Basically, one was like simple, short. It's quite biased. So basically, it assumes that like whatever I'm counting, like my value, if I have it wrong, it's gonna keep having bias. While Monte Carlo has like high variance. Basically, whatever this one path I took, there's multiple paths I can end up in, and that the values in these endpoints could be very different. So this leads us to, depending on which endpoint I end up in, so which return I get to there, then I might have variance in how I compute this value. Okay, and there's this like intermediate point where I can sort of figure out, I can trade off bias for variance. So maybe I can take more than one step, but I don't have to go all the way to terminal. So this gives us like basically more data points because I see more rewards in the future. But if the depth is very big, then I don't have to wait for it to end. Okay, so let's do a quick exercise. We have 8 episodes. Basically, I'm in state A, I'm gonna get reward 0. Then I go to state B, and I'm gonna get reward 0. My episode ends. And I'm in B, I get reward 1. And this happens 6 times. I'm in B, I get reward 1. And there's another episode where I'm in B, I get reward 0. So we can sort of see that the value of B, based on what I have here, so 2 times I got 0, 6 times I got 1, is 6 divided by 8, so it's 0.75. Now, what is the value of A? I'm gonna sort of give you a hint. So this is like, if we transpose the tree that we had on the previous slide, we just move it to 90 degrees. Basically from A, I had one episode that went to B and had reward 0. So what would Monte Carlo say in this case? What is the value of A? So that is I heard the 0 and I heard the 6 divided by 8. Basically for Monte Carlo, which tells me I'm gonna take one episode to the end, and the value is gonna be whatever I'm gathering there. So for Monte Carlo, it's gonna say it's 0. But for TD, which looks at the reward plus the value from getting whatever I get when I'm in the next state, so it's gonna be 0 to get to B plus whatever the value of B is. So that's gonna be 6 divided by 8. So shall we recap? MC does one episode to the end. I have exactly one episode, it gets 0. So then according to MC, the value of A is 0. For TD, I just look what is the reward and what is the value of the next state. The reward is 0, the value of the next state is 0.75. So then TD will say the value is 0.75. It could be that both are wrong. They have but in a way, they're also both correct. Like it's, one minimizes the error on the data it's in, and one solves the MDP that the data implies. But it's incomplete data, so we need more data to figure out what is the final value.
Could you go a little bit more in depth about why batch MC is 0?
Yeah, basically so let me go here. Basically for Monte Carlo, I'm gonna take one episode to the end. So far so good? Yeah, and then for A, I had exactly one episode, which was this A goes to A, takes 0, and then goes to B, has 0. So there's this one episode which ended, and then the return was 0 for that. So Monte Carlo will just estimate the return to be 0. It's what? What? I didn't hear.
Is it also possible if we go 0, then 1 in an episode?
Yes, yeah. So if I had other episodes for Monte Carlo, which is why it's high variance. Basically, if I took another path here, so if I went this way and my return would be 1, then Monte Carlo would give a different estimate. So depending on which episode I'm taking, Monte Carlo gives different estimates. That's why it's high variance. Okay. Okay, so let's put it all together. So we talked about temporal difference. It's like this sort of breadth first analogy. We have Monte Carlo, which is like depth first. We have dynamic programming, which assumes you have access to the transition function. So it assumes you can check multiple state actions. And then you have the exhaustive search. So this is like if you had unlimited budget and you could like take all the episodes until you explore all the states and all the actions, then you could compute the values. But realistically, we never do this. Okay, so now we know how to compute values. And we are saying that we're going to use the values to figure out how good a state is. Basically, we didn't like that the gradients were scaled by the whole return. We want to discriminate between good actions and bad actions. So we want to reinforce good actions with positive reinforcement and bad actions with negative reinforcement. So we have this, basically, I only talked about the value of state so far, but we can also compute the value of state action pairs. Whenever I put a star, it's an optimal policy or an optimal value or an optimal something. We saw this before. So basically for the optimal, if we can compute state values of state actions, which is quite similar in character to like the values of states. And we know like we computed it optimally. So we know we have like the ground truth of what the values of state actions are. Basically, we can figure out the best policy, the optimal policy, by taking the maximum action according to the state action value. So basically, I assume I have an oracle, tells me if I'm in this state and I take this action, it gives me 6. If I'm in this state and I take this other action, it gives me 9. If I take the second action because that gave me the higher value, then that will lead me to a greedy, like a good policy, the optimal policy. Yeah. Okay. So how do we learn this? It would be amazing if we had access to these state action values, but in reality, we don't really have access to them. We have to learn them. So no matter what the policy does, we imagine the best possible course of action. That's what we did by taking the max action. if we had like the grid word environment, somewhere where we can enumerate all the states and all the actions, then we can converge to the optimal value, state action value by just even taking random policies with enough budget. We'll eventually observe all the values. But with function approximation, so when we can't enumerate all the states and we have to learn the values, basically it's a bit complicated to estimate this, but it actually works for some things. Okay, so you notice that I'm saying let's take the maximum action. That means we're sort of diverging from following our policy. So this is the difference between on policy and off policy. When we learn about the policy we're currently executing, so we're always sampling from our policy, and that's the action we're taking, that's on policy. And that's SARSA and PPO. So PPO, we'll hear everything about it, maybe. But then when we don't take the actions the policy is saying, so we're off policy, then we can learn from any data. We can take it even one step further. We don't have to just take the maximum action. We can do like run epsilon greedy, so take random actions to be able to explore. We can do other things as well. So basically that leads to Q-learning. No matter what the policy does, choose the best action in this case. And then, as I was saying, if we want to explore, we can do epsilon greedy. We can take random actions, so not according to the policy. And because we're not acting we're not learning from the policy we're acting, we really can learn from any data. So this means that we can also use experience replays. We can store the data that we had in the past, and we can do multiple steps of gradient updates on it. And this is actually quite interesting because generally when we do supervised learning, we assume that we have the IID assumption. So basically SGD assumes independent samples. But when we act through an environment, there's no independence there, right? Like depending on if I'm in a bad state, like if I'm in a, like, I don't know, in a lake, all my neighboring states are gonna be in a lake. So there's no independence there. But if we do experience replay, we can sort of store the data and we can shuffle it. So we can sort of regain some of that independence assumption. So if we put this together, so we have this Q-learning, and we have experience replays, and we have target networks, which I'm going to explain in a second. Basically, we have the main ingredient of DQN, which you might have heard about because it was quite a big thing. It was like I guess the first time that a network was like so successful at playing Atari games. So I mentioned target networks. Basically, now we have this Q network that we're gathering data and we're sort of also trying to learn from it. So we have like a moving goalpost. So a trick that we're gonna see a few times is like, we're gonna freeze a network and we're gonna gather data with a frozen network. And then we're gonna update that frozen network later in the, like every n steps. So that we don't have to like sort of follow a moving goalpost. Okay. So we talked about value functions. We talked about state action value functions and how to learn them. Now, how do we go back to policy gradients, which is how we started. So how do we learn policies and how do we use these value functions to distinguish good states from bad states? So we're gonna use a baseline. Basically what this better than expected means is the agent is gonna estimate what we expect. So what is the value of the state? And we're gonna subtract that baseline from the return. So instead of, if you remember this, we're like having this gradient of the log of the probabilities. We're multiplied by the base, like by the return minus the baseline instead of just the baseline. Yeah, and because basically the gradient, like this, yeah, this, it's basically no bias. Okay, so what is this baseline? Let's define it, let's put it more formally, the advantage function. So it evaluates how much better than expected an action A is. So we're gonna look at the state action value compared to the value of that state. And this leads us to actor critic. So this is like quite a famous agent. This was also in the fusion RL agent that I was showing at the beginning. Basically, we're gonna have two parameters, so two networks we're gonna play with. We're gonna have the policy with parameters theta, and we're gonna have the critic. So that's gonna have its own, so that value function is gonna have its own parameters. We're gonna do the same as in reinforce. We're gonna play out a trajectory with the parameters theta, and we're gonna compute values and advantages. So when we're computing the values and advantages, we're sort of, we've seen this formula for computing values, and we know that the advantages are the state action values minus the value of the state values. And then we're gonna update both the actor, so the policy, and the critic. The critic basically is supervised learning. Basically, we just have these differences that we're doing like mean squared error on. Okay. Shall we recap? We have a network that learns how to act, and a network that learns how to estimate values. The network that learns how to estimate values, we can use it to get a better scale for what is a good action and what is not. So you can notice it here. Basically, now we're scaling the log probabilities with the advantages rather than the return. Okay. Yeah.
All of this depends kind of on the reward being available, right? So what if the reward is not there? So would it like collapse, like both the networks collapse, or what happens?
What do you,
like there is no RT plus I basically, like the environment doesn't give you reward for either the terminal state or any in between. Then this whole framework collapses, or still it learns something.
Oh, so I think that the assumption of the problem is that at each step we'll have a reward. Basically, if you remember the way we were thinking of trajectories, you have state 0, action 0, reward 0. The reward might be 0 in a lot of the cases, and that's how a lot of the environments are defined. When we don't really have signal, it's just like 0 reward. So I guess it's like part of the problem definition that at each step we'll have a reward.
And another thing is, if RT plus I is almost everywhere 0 and just has a terminal state, then does it take long time to converge, or what happens?
Yeah, so that's actually like that's a thing where like we have like inefficiency of RL. We generally see that the denser the reward, you basically have more signal to learn from. You can distinguish between actions faster. If all actions give you 0, then there's like it's hard to know which actions are good actions and which actions are not. So you'll need more data to figure out what leads to a good outcome or not. Yeah, so your intuition is good on that.
Thank you so much.
The actor and the critic network, do you train them differently, or like?
So they get separate updates.
Yeah, do they have like different weights in?
Yes,
they can be.
They each have their own weights. So the actor has its own weights, and the omega, and the theta, and the critic has the omega weights.
So like the performance of the critic, it also affects the performance of the.
Yes, for sure. So basically, if you're not able to distinguish between like this scaling by disadvantages, might be like not accurate. Yeah. That's very well pointed. So I'll just repeat what he said. Basically, if it's hard to learn a good critic, it's gonna be hard to figure out a good policy. Okay, so we saw in like Monte Carlo and TD that we had this like bias variance trade-off. So depending on how far ahead we look, we're gonna have like less bias if we look further ahead. But if we just look at one episode, we're gonna have higher variance. So sort of the same problem, because that is how we estimate values, you can sort of expect it to transfer to how we estimate advantages. They have their own bias variance trade-off. And we're seeing there, like we could do this n steps TD. We can sort of do something similar for this. So we can do like the lambda for the advantage as well. So if lambda is 0, we have the high bias. So this is like the sort of the TD equivalent. We have the high bias and low variance. And if lambda is 1, we have the low bias and high variance. That sort of like leads us all the way to the end. Okay, so we talked about advantages. Now let's see what are some other problems with reinforce. Basically, to avoid like early convergence, like let's think about back to our slot machines. Like I could try one arm and I see it's good. It gives me like a reward. And I can just like keep trying that arm and I won't even try the other arms. So in that case, my policy will sort of peak, will say that my probability of taking that one action is 1, and the probability of taking the other actions is 0 because I haven't tried, I'm not taking it. Or the one time I tried it, it was bad, so I'm not gonna try again. So what this means is that maybe that arm I initially took was not the best arm. And I should be encouraged and I should encourage agents to explore. So this means that I want to have like a less picky distribution where I give each action a chance. So we can think of it as like favoring more chaotic policies. And when we think of chaos, we think of entropy. So what is entropy? Basically, entropy defines how much information we learn when we see the value of X. So if I have a fair coin, basically, whenever I flip the coin, I don't know what the outcome will be. So that is the highest entropy. If I have a biased coin, so if I know that whenever I flip it, I'll get heads, that is 0 entropy because I know I'll get heads. So it's sort of, it's on this curve. Like the two ends have 0 entropy. The fair coin has like maximum entropy I could get. And this is a useful concept in policy gradient methods. So we can use entropy of a policy to encourage exploration. So we're gonna say, okay, estimate the entropy of the policy and scale it by some factor beta, which at the beginning, maybe I want it to be high. So I want to have more exploration at the beginning to try more things. And then the more I try, the more I know what is good, I can say, okay, now we can reduce so we can have less chaotic policies. Okay, so that is solved. We have one way of encouraging exploration when we have policy gradient methods. But there's some other problem with policy gradient methods. So basically the fact that the data comes directly from the current policy means that if I'm in a bad policy, I'm gonna get bad data. And this is like a sort of a slippery slope. For example, let's say I have a good policy, I keep gathering return, but then I take one bad update, my policy gets worse, and then the data I'm gonna generate is gonna get worse. So if I have one update step which is too large, it breaks the policy's behavior, and then the next data is gonna be bad, and then it's gonna lead to a worse and worse policy. So how do I do this? Basically, I want to make sure that I can't take too large steps, that I'm always gonna stay like within some confidence interval of where I'm at. So trans-region policy optimization is like this variant of a policy gradient method, which uses a constraint optimization problem. Basically, I'm gonna make a surrogate objective, which is gonna say, whatever my new policy is, it can't be too far from my old policy. So I'm gonna put a KL factor on it. And this is, I mean, this was used for quite a while, but then came a new version, which is PPO. And this you probably heard, it was like quite used with LLMs. It's got RL working with LLMs at the beginning. So basically, instead of doing the KL divergence, which is quite an expensive factor to compute, we're gonna use clipping instead. So we're gonna compute the ratio of the new policy to the old policy, and we're gonna say it can't be too far, like let's say 1 plus epsilon, 1 minus epsilon. That is like my interval where my ratio can be. So, okay, we're good at time. Basically, we've seen all parts that lead to PPO. And I think you're gonna even see it in practice maybe later today at the tutorial. But let's recap. Basically, because we're on policy, we can't like train on any data, but we can do several epochs on per batch of data. So we can gather trajectories and we can train like usually like 4 epochs, let's say, on the batch of data. We can use the normalized advantages. So I'm not gonna go back, the ones where I'm looking at the state action value and the action value. And we can use the critic, basically the value loss, and the entropy bonus that we talked about to encourage exploration. And when we combine all of this is what leads to PPO. Okay. Okay, so let's see how what RL looks like nowadays. Basically, in RL from human feedback, we had this thing where we had humans say what do they prefer from an LLM output. So the reward moves from a learned model of human preferences, which is what we used for some time in LLMs, to something that we can simply check. So verifiable rewards. And you might have heard about the DeepSeek R1. This was one of the models that used verifiable rewards. Basically, it uses like things it can run and it can test. So, for example, if it computes like a math equation, that can be correct or incorrect. If it runs like a code test, again, it will get an error or not. So this transition to verifiable rewards is cheaper because you don't need humans to label. It's harder to hack because it's not really like figuring out some niche preference in human data. So like, I don't know, always complimenting the user or something like that. And it's scalable because we can generate a lot of tests and a lot of math tests as well. So I mentioned DeepSeek. Basically, this was, quite it made quite an impact when it came out. It uses, one of the things that it was like, I guess, new at that point. It uses strict deterministic verifier. So what we were saying about test cases for code, final results for math, and it has like format constraints with tags. So I think it's like more structure in a way. And then the other thing which was quite different. So before we always had like supervised fine tuning on top of an LLM. Now this was quite different because it just had RL on top of the base model. And the author saw that it already has like interesting behavior emerging from this. So it had like aha moments. You can see it here. Basically, it was computing something and it says like, wait, that's an aha moment I can flag there. So it's quite interesting that the agent learned this sort of reasoning itself, this chain of thought. I think now, I mean, I've seen this in a lot of LLMs, so now this is not that new. And yeah, it can also do self-correction. And the other thing that they were mentioning in the DeepSeek paper and some other papers is, interestingly enough, like moving from PPO to something that doesn't have a critic anymore. So I guess we're moving from PPO back to something that's like familiar to reinforce. So PPO has to maintain parameters, gradients, optimizer states for a critic model, and that's expensive because that's usually like significant, maybe equal in size to the policy model. But in GRPO, we basically sample a group of answers, we score them, and then you see here, we subtract the mean and divide by the variance. So this doesn't need a critic network, it's cheaper, it's faster. It was one of the main benefits of this. And if you remember, we were talking about environments many slides ago. Basically, we have like the simple environment, but now we can have also environments that are automatically generated. So in dynamic programming, we had like the explicit transition function. One such word model that is like learned by a neural network that's quite impressive, like Genie3, learns implicit dynamics directly from data. So it basically sees a lot of data and it generates like interactive 3D states. So what this looks like is basically you can map a text prompt to a word. So I think here it says skiing in the Alps, about to take a jump, and it simulates a ramp with snow, and in that environment, you have arrows, so you can say like left, right, and then basically the simulation will change based on what your actions are. So you have like a live environment. And I think the other one was like you're on a horse riding or something like that, and you can see the years of the horse. Okay, so I guess the current strength of RL agent is now in post-training. So the way most LLMs are formed are like they have like a big foundation model with a big pre-train, and there's like a later stage which is like the RL post-training. And it's actually quite similar in robotics, even if I'm not talking about it there. Here it's quite interesting to look at. And our experiment, unfortunately, but I promise I'm gonna send you like a demo of it so that you can see how it developed like. Okay, so even if this bandit would have trained on your votes, there were still like quite some interesting things to keep in mind. And I think these are interesting for me to think of like what would the bandits struggle with, because these are also like problems the agents struggle with any reinforcement in the real world. Basically, reward has a lot of confounders. So in this case, you could have voted negative on a slide because you didn't like the content, even if you like the style, which is what the bandit was trying to learn. And then there's non-stationarity of the reward. So if you were stopping to vote or something like that, then basically the agent was getting less reward, but that wasn't because of its behavior. So the reward could have been noisy. And again, you see this in the real world. There's a lot of noise in figuring out the reward. And yeah, basically a lot of assumptions on like the things being independent. The reward is not always coming from independent things. Yeah, so I will share this on Slack together with resources of things I talked about, and credits to previous iterations of EEML, which have helped me build this stack. There's also a notation cheat sheet. So if you wanna just put it together, take a look again at what we talked about. And if you wanna look in more depth on how we compute the gradients in policy gradient methods, there's also a derivation. So yeah, I think that's it. Thank you.
Okay, so we're going to get a few questions.
Thank you for the talk. So when we apply RL to language models and world models, I guess, how do we get around the fact that these environments are totally non-Markovian?
So I guess, so for example, in Atari, which was like something where it wasn't Markovian, people used to stack like 4 frames together. And there's like a bunch of hacks we can do. I think they're like mostly like engineering hacks to make the algorithms work, but the algorithms stay the same. So we have this assumed in the math. Yeah, it's not a very satisfying answer.
Thank you.
Okay, so first of all, thank you for the talk. Secondly, I'm curious, what are the ways in which we can handle very sparse rewards? So for example, if you have a very large grid and you have only a single reward, the reward is very sparse and you have to take a lot of actions. And I read at some point about a thing called intrinsic curiosity or something like that, but I want to hear your thoughts on handling sparse rewards in general.
Yeah, so I guess I didn't go in depth about it, but there are some things that like you need to be more careful with RL than with supervised learning. So generally, like for example, learning rate. So if you have sparse reward and you're noticing something, taking a big step can lead you in the wrong direction. So you need like generally lower learning rates and things like that. But also you can define like proxy reward functions. So like yeah, you can I don't know, like learn a model at the same time or something like that. So figure out like some other ways to learn about the environment that are complementing the reward function. But I guess it's like it's an inherent problem, the sparsity of the reward function.
Thanks. Thank you for the talk. So my question here is what we are seeing now with the progress in the agentic AI, how that will improve or can improve the reinforcement learning, and how that is linked between the reinforcement learning and the agentic AI we have now, progress we have now.
That's a good question. I don't have a. I guess like the things I'm noticing, which is like I'm noticing like this, the agents have these like more and more powerful harnesses. So for example, I was saying that I'm seeing like the RL from verifiable rewards is getting more and more adopted. But if you interact with an agent nowadays, like it's, for example, you tell it to implement something, it's gonna have these things where it's gonna run tests and things like that in it by itself, sort of by default. So we're also seeing like this, like, I guess like at test time, new behaviors because they have this like intuition baked in now. So I guess that's what I'm noticing, but I don't know. I guess we'll see.
Any other questions from anyone?
Hi, good talk. Is it possible to over-engineer the reward?
For sure, yeah. Yes. And agents are known to find shortcuts in the rewards. So in a way, like if you're, I don't know, you're giving a reward for something that is not really the behavior you want learned, the agent will like optimize that. I'm trying to think of some famous, there were some famous examples, but yeah, sorry, doesn't come to mind now.
Hi, thank you for your lecture. I'm wondering about future of RL for tuning the LLMs. We use this mechanism of aligning LLMs to our preferences right now and to preferences of some environments. And I'm wondering what is your opinion on what is the future of RL? Are we going to focus on designing the reward models and the environments more carefully, or maybe we should focus on something more general, or like find a way how the environments return these rewards?
Yeah, I quite like this like verifiable rewards. I think that's like one way to scale them that doesn't change in a way. Like with human preferences, it can change on the data you're gathering every time. Like I guess you can see the models are changing. So if you try to gather preferences on a new model, sort of your preferences will change because now like maybe it's less verbose. So you're gonna downgrade less verbosity, but maybe it's like not giving sources as much or something like that. So it's sort of like preferences are a moving target, while verifiable things are correct or incorrect. So I quite like that. I think, yeah, similar to what I was saying earlier, like I'm seeing a lot of power coming from the harnesses around the agent. So I think that's something that we're going to see more of probably.
Any other questions?
Hi, great talk. I'm not really into the reinforcement learning, but you mentioned like foundation models. I know that in a computer vision, they learn some like features, valuable features that can extract from the image. But I guess that foundation model for reinforcement learning, it depends on the task, right? So what can the foundation model be made for a different task, and what do they learn?
It's not loading, but basically, yeah, like in Unity, you have like a multimodal, like text and image. So you have like a different foundation model. I guess in DeepSeek, it's like a language. So yeah, you can have depending on, I guess these are the two common ones I know of.
Any other questions? I'll actually ask a question myself. Like in LLMs, when they do RLHF, like I feel the RL algorithms that are using are way simpler than what we used in other spaces. So curious sort of what you think the reason for it is. I have my own opinions, but I'm curious sort of like what your perspective is, like what's going on, why are we giving up some of these advances that we've done at some point?
I think that's a really good question. And I was listening to this, I think, talk where they were saying like all these advances in RL that were meant for planning long term and things like that, we're not benefiting from them. So how would it be if we're compounding that? But I guess it's to me it's mostly a thing of convenience. It was probably easier to get PPO working than it was to get the complex agent working on top of that. But yeah, if you have another thought, I would also be curious to hear it.
Yeah, I mean, just to like, I think there's something about the value function as well in LLMs where I think it's not as easy to learn, while the policy it's much easier. So therefore, methods that don't actually rely on bootstrapping as much sometimes work just better because, but it also probably says something about the environment, which is it's not as interesting as we think compared to others.
Yeah.
Any questions? Oh, yes.
Hi. You presented that we went from RL from human feedback to RL from verifiable reward. Some labs are now doing RL from non-verifiable reward with some kind of rubrics. Do you have like an idea or intuition or where like are we going to, like what is like the main direction RL is going to take to like improve LLMs?
I don't know, I guess not sure from the RL point of view. I mean, I guess I'm seeing the like a big frontier of improving is like on the efficiency side, and that's where like what I've been reading recently. But yeah, I'm not sure on the RL side like where it will go next.
So Andrea is going to be around for most of the school, I think until Friday. So if you have more questions or you want to discuss RL topics, feel free to bother her when you see her around. We're going to stop here to have 20 minutes break, more or less, for coffee. Let's thank our speaker again. And try to be back by 11:20. So we're gonna start in a few minutes. If people could take a seat and okay, so it's my great pleasure to introduce our next speaker, Kuyung Cho. The first name is always hard for me. So I know Kuyung for a really long time. So when I was doing my PhD in Montreal, Kuyung was doing a postdoc. And a lot of my first papers were actually co-authored with him. And he acted as a mentor for me in those early years, basically helped me figure out how to do research. So he's extremely good at that. So if you have a chance to talk to him, he's really good at giving advice and guiding people and sort of getting them through hard periods. So I definitely encourage you talking to him. After the postdoc, he went to NYU, where he was a professor. Then at some point, he started a company in drug discovery, GeneTech, or present that was then, anyway, long story short. But now he's back at NYU, where he has been doing amazing work, ranging from language modeling, NLP. So he's one of the key co-authors of the first attention paper with Dima and others. And then moving more and more towards drug discovery and AI for science in sort of the later years. And he decided to change the topic of the talk. So I actually have no idea what the talk is going to be about, but shortly it's supposed to be statistics upside down, and he'll explain what that means. So with that, I'll leave it to you.
Thank you. Thanks for the great introduction, and also great to be here. In fact, I tried to come to EEML 3 times, and then first 2 times I failed because I booked the wrong flight first time. Second time, I had an issue with my passport, forgot to actually get the passport renewed in time. So actually, my wife, who was then a girlfriend, was here 2 years ago in Novi Sad, but I wasn't there, unfortunately. But this time, finally, I'm here in person. I'm very happy to be here. And then, whenever you go to a summer school, what you notice is that every summer school needs to have at least one wacko who's going to talk about some crazy stuff so that there is going to be some, bar that we can set that is low enough for every other lecturers to feel much more confident and then easy to disseminate their message. So I thought I was going to be the one. I'm going to tell you a bit about the statistics, but how we should look at statistics from in this kind of computation oriented era. But before that, it was a great lecture this morning. Andreas actually gave a full, let's say, course from going from the Bellman equation all the way to the more recent, let's say, approaches to the reinforcement learning and language models. And I noticed one example there where, when she introduced the Bellman equation, you had to get the root or the distance from the Kotor to, let's say, Podgorica, we can actually look at the strategy because we are actually in the middle. And then we looked at it as, oh, what's the distance there? We're going to just add them up to the next distance. We get the overall distance. Great. However, behind every successful computational algorithms sits a successful representation and abstraction. I'm not going to talk about these 2 topics, but I hope you're going to always keep in your mind that it's actually all about the abstraction and the representation. Why is that? So I drove from Kotor to Settinji yesterday morning, and then I looked at Google Maps, and then Google Map told me that okay, there are 3 alternative routes. And I decided to take the shortest one according to the Google Map. And I didn't want to take a longer route, doesn't make any sense. And I started driving. And then I realized, I didn't know, but I realized at some point that it was getting really, really difficult to drive. And then this actually turned out to be a very famous route that you shouldn't take actually unless you live here. Took me a long time to get here, but this really tells us that how we abstract out things really sometimes leaves the details that matter. So we have to be very careful about the abstraction and representation. And then of course, I blame the Petar because he always talks about how his algorithm works on the Google Maps, right? And this is what Petar actually led me to. It wasn't easy. I think my wife kind of threw up as well while I was driving. But anyway, so the representation, very important, abstraction, very important, but I'm not going to talk about that today. In fact, I'm going to start by talking about the standard deviation. So who hasn't actually learned of standard deviation yet? Let's raise your hand. It's impossible, right? So we all learned about the standard deviation. And then even if we haven't actually looked at the formal definition of the standard deviation, you see that it's used everywhere. You see some of the news articles, they talk about the standard deviation. They said, oh, it's the 6th standard deviation away from the mean or something like that. But let's look at the standard deviation a bit more carefully today. So standard deviation is defined as the square root of the expected deviation that is measured using a squared, let's say, Euclidean distance of the individual items from the mean, that is the expected value of that thing. And then how do we actually estimate it in real life when we get a bunch of samples? I'm going to think about just the real numbers. Then I'm going to first compute the mean, right? So I'm going to compute the average. I'm going to subtract that average from each and every numbers, square the differences, and I'm going to average or compute the average of those differences and compute the square root there. And then this is what we often refer to as a sample standard deviation, because this is a standard deviation that is computed using the set of the samples, not the actual distribution. And then the funny thing about the standard deviation, despite the fact that it's really a useless quantity, is that this is a bias estimator of the true population standard deviation. So true population standard deviation was a standard deviation of the actual distribution. Why is that? The reason is because of the square root that is outside the expectation. If the square root wasn't there, that is a variance, then we know that the sample variance is going to be unbiased estimate of the true population variance. But because of the square root, which is a nonlinear function, suddenly the sample standard deviation is not a good estimate or the unbiased estimate of the population standard deviation. I only learned about it 3 years ago. I cannot believe it. I never thought about it because no one really should think about it. But of course, people have thought about it. On the internet, everything is written down. There's even a page on Wikipedia titled Unbiased Estimation of Standard Deviation that tells us that it's actually not possible if you actually don't put any kind of constraint on what kind of distributions we're thinking about. If we know which distribution we're thinking about, we can always come up with some kind of correction factor. So then my good colleague and my collaborator, Maxime, I started to think of, well, can we actually design an estimator of a population standard deviation? Just out of pure curiosity, right? That's a nice thing about being a PhD student or the professor, is that we can do these kind of random stuff once in a while. So we're like, okay, I want to do this. And then, when we start thinking about how to design an estimator, we need to, of course, go all the way down to the foundations and then think about what is considered a good estimator. We need to answer this question. One is that we want to have a low bias. That is that if I try to compute the estimation, and if I look at the expected value of this estimate, that has to be really, really close to the true value. We want it to be 0 effectively. And then we also want to have a very low variance. That is that every time I re-estimate this value, and then look at the variance of that. So we want the variance to be very low. If the variance is too large, we can't really use it because that's going to be unreliable. If the bias is too large, we can't use it because I know that I really didn't estimate what I wanted. And then sample standard deviation is a bias estimate. So the bias is going to be pretty big. Actually, it's going to be often it's going to be underestimated. So it's going to be negative, but the variance is actually relatively low. And then again, because of the nonlinearity that exists outside the expectation. So then the question is, how can I get a better estimator than the sample standard deviation that's going to have a lower bias and also the lower variance? That's a deep question, right? And if you recall, again, from the machine learning 101, or maybe the Sarath actually taught you yesterday, did he? Probably not. There is a concept called the mean square error. And then there's a concept that derives from the mean square error called the decomposition of the bias and the variance. So if you're trying to minimize the mean square error, eventually we're going to get to the point where the variance is minimized and then squared bias is also minimized as well. I mean, this is a very simple thing, but looking at this one, you start seeing that in fact, what we thought were really important for any kind of good estimator, that is having a lower variance and then lower bias, corresponds to minimize the mean square error as well. And the mean square error is one of the things that we always learn and we always try at the very beginning when we try to build a so-called linear regression or the nonlinear regression model. Okay, so then let's see. So instead of, so then you have to, what does it mean? Finding an estimator, good estimator, can be thought of as minimizing the mean square error of the estimator F that takes as input the data set. if I had a bunch of the data set paired together with the true population standard deviation, then I can use that to estimate the mean square error, which doesn't have the nonlinearity, so we can actually estimate really well. And then trying to find the algorithm F, the estimator F, that's going to minimize the mean square error, thereby is going to have a very low bias or the squared bias and a low variance as well. And then, looking at this one, what you notice is that that's actually exactly what we do almost every day. You can use MSE, you can use another, let's say, a criterion there as well. This is just training a neural network. You train a neural net that takes as input the data set, the set of the samples, and then you train this neural net to output an estimate of the true population standard deviation. And then if you train this model to minimize the mean square error, then that is going to give us an estimator that's going to have a low bias and also, or the squared bias and low variance as well. So perhaps that's what we should do. Instead of trying to be very, very ingenious and then trying to come up with a new estimator out of nowhere, why not letting the learning algorithm find the estimator for us? So we need to do a couple of things. One is that we're going to now define a prior over the problem space. That's the distribution space. And then from the prior, we're going to sample a distribution and we're going to sample a number of the samples. The number can actually vary from this distribution. And then because we actually chose the distribution or the prior over the distribution, we actually know the true standard deviation. Thereby, we can simply minimize the mean square error and then to find the F, the estimator. And this is exactly what we do. We define the data distribution. That's going to distribution over the distributions in this case. We define the input as a set of samples drawn from that, the one particular data points that we have drawn. And the output is going to a real value, just a single number. And loss means square error. Very simple, straightforward. So I actually asked Cursor to implement the whole thing and then show me whether it's going to work or not. And then how are we going to do that? We need to make one decision. That is, how we are going to parameterize this function f. So this function f, the estimator, we know a few, let's say, properties that we want this function to satisfy. One is that if we want it to be permutation invariant, we don't want it to change the output depending on the order of the samples. That is only for the standard deviation. Later on, we're going to see the cases where we actually care about the ordering as well. And then we want it to output a single scalar. And then, of course, you can think about normal transformer, but probably we need to remove the positional embedding. And then we can use so-called set transformers or any other types of this kind of, let's say, data set level predictor. In fact, we have a speaker here tomorrow who's not going to talk about this one, but who actually worked on this particular direction. So you should actually ask her about it. But there are many options, finally, that can actually be used for this kind of purpose of the data set level prediction. So let's say in our case, we're going to use the set transformer plus plus. So I asked Cursor, oh, hey, they try to, let's say, come up with some, let's say, nice, let's say, proof of concept to run these experiments and then show me whether we can actually find the estimator of the population standard deviation that is better than sample standard deviation. And then Cursor actually suggests me that, okay, let's define a prior over the problem space by looking at a mixture of two Gaussians, because we can actually compute the exact population standard deviation directly. And then let's try to test the estimator. It's just like any kind of machine learning algorithms on the distributions that are somewhat different from the training distributions. One group of the distributions is going to be a log normal distributions. The other group is going to consist of the heavier tail, more skewed, let's say, distributions. And we just train a two-layer set transformer plus plus with the atom W. And it's really straightforward. It's just a one file it actually generates. And what is really interesting is that it actually does work as we anticipated. So let's look at this part. So np.std DDOF0 is where you compute the sample standard deviation, but the denominator is going to be just a 1 over n rather than -1. DDOF1 is going to do the bezel correction, so we actually use the 1 over n minus 1. And then this is a set transformer that has been trained on a slightly different set of the distributions. And what you see is that this is the bias. Now, this is all, let's say, synthetic problem. We can actually compute it. And then what you see is that indeed, set transformer plus plus gets you the estimate of the population standard deviation that is more or less unbiased. On the other hand, as anticipated, the very simple sample standard deviation estimators tends to underestimate the standard deviation, that's because of the square root, right? Square root is going to eventually, let's say, slow down a bit. And then thereby you do see that it's underestimating. And even better, because we train or we find the set transformer plus based estimator using a finite number of samples, what you see is that the variance is much, much smaller than the existing, let's say, sample standard deviation estimators. And then what this really tells us is that somehow set transformer plus is estimating the population standard deviation. It also works on the log normal distribution, although they actually do degrade a bit as it gets further and further away from the original training distribution. But what it actually tells us is that maybe a better way to think about how to come up or the designing an estimator is not to think about it as a designing an estimator, but trying to search for an estimator using a systematic methods that we have all discovered over the past, let's say, several decades, especially in the field of machine learning. And then, I mean, how does it do it? I have absolutely no idea. I have some speculations. And generally, I'm on the side of, if we are working with the black boxes, let them continue to be black boxes. I don't think it makes sense to try to open it and then look at it. That's going to always mislead us. But it is solving this problem in a way that is very different from how people have been solving. How people are solving it is to think about the actual generative process, which distribution I'm working with, make this strong assumption, and then trying to figure out what is the right way to correct the standard deviation or the sample standard deviation. But this model is doing something different. Maybe it's doing the same thing. However, it's doing it in an extremely, extremely efficient manner. But starting from here, then you start thinking about what are the kind of new estimators or the inference algorithms that we can actually design without actually having to design them ourselves. One example that I want to bring up is a mutual information. Mutual information is the quantity in statistics. It measures how two random variables are dependent on each other in a nonlinear way. And then in other words, it measures a nonlinear statistical independence between two variables. Why is it the, let's say, quantity? Because if I can tell if any pair of the random variables are independent of each other, I can essentially solve almost every problem that you can ever imagine, from the causal discovery, causal inference, all the way to any kind of, let's say, quantity that you want to estimate. But unfortunately, because of this, kind of useless as well. But it's an interesting quantity to think about. Let's think about what mutual information is. Mutual information between the variable x and y is defined as the expected log ratio between the joint density of x and y and the product of the marginal densities of x and y respectively. And then this looks kind of, let's say, reasonable, right? So if x and y were independent truly, then p of x and y should be p of x times a p of y. So thereby it's going to log of 1 is going to be 0 if they're independent. Otherwise, it's going to change. But it's really difficult to estimate it because of this, again, the nonlinear nature. If we decide that it's going to be linear, then it's very easy. It's just a correlation. But it's very difficult to compute it. And in fact, one of the difficulties that we run into when we're trying to design an estimator of the mutual information is this our preconception. Because mutual information is defined in this particular way, that is defined in terms of the expected log density or defined using all those density functions, we get stuck at this point where we say that, okay, we know to solve this problem, we gotta solve the problem of the density estimation or the density ratio estimation. And these two problems are super difficult. In fact, yesterday, Sander talked about the diffusion models. The reason why we got to diffusion model, starting from the denoising autoencoders and whatnot in, let's say, 2008 or so, over the past, let's say, essentially 20 years, is because we still don't know how to solve this density estimation problem well enough. But if I have to solve the density estimation to estimate the mutual information, then we're kind of doomed from the very beginning, which is kind of a weird thing, right? Because density, you can see why it's difficult. I need to be able to make a gigantic table, or I need to make a function that's going to compute a single number that is the density of the pair of x and y values for every possible values. Obviously, it's going to be difficult. But mutual information is just a single value that comes out of a pair of the random variables. So if you think about it, it seems like we're trying to solve a more difficult problem to solve a less difficult problem. So before I talk a bit about the mutual information, it's a good idea to talk about the uncertainty, because one of the things that the statisticians always tell me is that, well, what you say doesn't make any sense because we really don't care about the point estimate. We always care about the uncertainty. I was like, sure, okay. Because at the end of the day, I want to actually disagree with the statisticians on that aspect, because point estimate is great, because it really is the number that we can actually throw around, or we can look at it. But I do agree with them in a sense that when it comes to decision making based on the statistical estimates, it's really important and helpful to know how certain we are about these estimates. And that's going to actually change how we're going to make a decision. We learned about the reinforcement learning. When it comes to decision making, we have to be somewhat optimistic, but how optimistic is going to be based on the quantified or the estimated uncertainty. There are many different ways to estimate the uncertainty. In simple statistics, my favorite is just a bootstrap resampling. If you have a bunch of data points, just resample them over and over, get the estimates, and then see how the estimates actually look like. And then I prefer to look at quantiles rather than looking at the exact numbers. Are they well actually calibrated? It turned out that the Natasha Tagasovska, who I think they gave a lecture here at some point many years ago. Anyway, and together with the David Lopez Paz in 2019, showed that we can actually train a neural net to not only estimate the mean of the target, but also any kind of quantile. So Qth quantile, and then they called it a simultaneous quantile regression using a pinball loss. This loss is really simple to implement. It's like the one-liner in PyTorch or JAX or whatnot you use. And it's relatively straightforward to show that by minimizing this pinball loss, you actually end up training a neural net that is able to predict all those Qth quantile rather than just a single estimate that is the mean. And then this really gives us a superpower because we don't now have to worry about the uncertainty estimation of our estimates. We're going to train our estimator to output the full quantile of the potential estimates. This is what I just said, but there's one issue that I'm going to talk about later on, is that there are many different types of the uncertainty, but this really gives us like 90% of the things that we need. I'll show you what I mean by this soon. So let's come back to the mutual information. Of course, one of the biggest issues in this scheme of, let's say, training an estimator is that we have to define a prior over the problem space so that we can actually minimize the expected mean square error over the prior. Fortunately, in 2023, Pavel and Grabowski et al. From the Zurich, I think, ETH, proposed a really nice procedure to stochastically generate a set of samples from complex distribution while we know the mutual information exactly. And it's a very straightforward thing. Looking back, it's very trivial, but the idea is that I start from the bivariate normal distribution, for which we often know the mutual information because they only have the up to the second moments. So we just do the CCA and then we can actually get the mutual information exactly. And then for each of the random variables or the samples of the random variables, we're going to apply a invertible but highly nonlinear function, such as the normalizing flow and whatnot. And then that actually gets us a set of samples that are drawn from a very complex distribution, but we know the mutual information between those two random variables exactly. And it's a nice thing that arises from the fact that the mutual information is measuring the nonlinear independence rather than the linear independence. So they actually came up with this procedure and then put out a very nice open source package in order to produce a large set of examples to evaluate existing mutual information estimators. But then we were reading about this paper and then realized that, hold on, if there are a lot of examples, right, that they were using to evaluate many of the existing estimators, what do you need to do? Next step is to use it as a training set. And then we're going to find the estimator that's going to work well on all those complicated problems. More specifically, we use the exactly same procedure to produce a large set of the very realistic problems. Sample sizes will vary from 10 to 500. Dimensionality will vary from 2 to 32 dimensions. Mutual information is going to vary the wide range, going from the 0 to 40 nuts, which is actually massive. And then also the diversity. We actually look at all those different ways to produce the complex distributions. Now, of course, we're going to separate them out into training, validation, and test set. And then we're going to use this to train a single neural net that is able to estimate the mutual information of a set of samples, or the set of pair samples that follow any of these properties or satisfy all these properties. So what do? We use the attention over two axes. We use attention everywhere, and then somehow it kind of works pretty well. I love it. And then we're going to do the quantile regression on top in order to make an estimator that's not going to give us just a mean or the point estimate, but the entire spectrum of the quantiles of the mutual information. So the idea is relatively simple, right? I mean, at the end, the execution is even simpler because training this neural net has become and then is increasingly more becoming standardized. So we're going to just rely on this standardized systematic procedure in order to search for an estimator that works really well. And I can tell you the answer here is that it just works. So we tried against all those different existing estimators, starting from the CCA. CCA is the optimal estimator if you're working with the normal variables. And then we have a KSG that's based on the nearest neighbor structure. InfoNC, InfoNet, these models are trained on neural net in order to, in fact, estimate the mutual information. The darker color means that the bias or the excess MSE loss is really, really large. And then what you're seeing at the bottom are the missed, we call it missed mutual information by supervised training. Then what we see is that they actually do get us a much better estimate of the mutual information than any of the existing estimators. And in fact, some of the estimators just don't work in this kind of setup that we have, like 32 dimension. 32 dimension seems really small nowadays, but it's a massive dimension if you want to estimate the independence, because you need the exponential number of samples. That's what we think, right? In order to estimate the density, you need the exponential number of samples. That's the curse of dimensionality. So some of these estimators simply fail. But when we compare against estimators that did not fail dramatically, then we still see that this neural net that we trained somehow is the better estimator than most of the other things that we have compared against. And then, in fact, that's true for the bias as well as the variance. So KSG is a really nice estimator. This is the only one that I will say that actually worked before. But then compared to KSG, MIST actually gets you a lower bias as well as a lower variance across the board. And furthermore, because MIST doesn't solve the problem of the density estimation, which actually does require a lot of samples, the number of the data points that you need in order to achieve a certain level of the accuracy or the certain level of the bias actually is more or less flat as the dimensionality grows. On the other hand, KSG, which does some kind of density estimation using a nearest neighbor structure, as you can see, the number of the samples you need in order to get to the same level of the quality actually grows quite rapidly. And then sometimes we just cannot actually control for it as well. With a very low tolerance, we couldn't actually find the right number that the KSG in fact converges to. So what that means is that this is one of those algorithmic traits that you can imagine that tells us that the estimator that we found by this kind of systematic search procedure found a solution that doesn't rely on the density estimation or the density ratio estimation. And this is really cool thing. I don't know what is happening inside, but this estimator works better than most of the other existing estimators, some of which were in fact invented by some of the people in Montreal, Mila as well. I don't think anyone who had invented them actually are here. But it turned out just a stochastic gradient descent was able to find a better algorithm than the very brilliant, let's say, minds that we all work together with and so on. And furthermore, it actually generalized to the unseen dimensions. So the dimensions that were not seen during training time, as well as the unseen number of examples as well. Now, of course, generalization is not perfect. Obviously, we define the prior. So if it goes too far away from the prior, it starts to degrade as well. However, as long as it's somewhat near the prior, it just works much better, again, than the traditional estimators. And some people say that, well, you have to define the prior. But they all forget to realize that all the existing estimators all come with the extremely strict and often not falsifiable set of assumptions. So you can almost think of it as we're trading off the necessity of the assumptions together with the necessity of the prior over the problem space. And then this can be used for the feature selection, not really important. If you want to do the feature selection, there are so many better ways to do it, so you don't have to do this one. But this is just a demonstration that once you train this estimator can be used for many different purposes as well. And then I forgot to mention about the uncertainty. So we just train with a quantile regression. Now, let's say I'm going to use this MIST, the model that was trained with the mean square error criterion. And I'm going to use my previous, let's say, favorite method. There's a bootstrap resampling. And then this is a calibration curve. What you want is that you want your methods to lie on this linear line. However, what you see is that if you look at the missed MAE 0.090 with the bootstrap resampling, what you see is that yes, when the values are on the lower end, they're well calibrated, but eventually it's miscalibrated. But by training a model with a quantile regression, we get almost perfect calibration, essentially for free. When we are thinking about the distributions of the problems that are way out of the training distribution or the prior distribution, we do see that there will be a bit of a miscalibration, but still you do see that this is still much better than any of the existing estimators. And then it's always going to underestimate this because we're working with a neural net that has a kind of finite dynamic range there. But what we see is that this approach is really nice. Often you can come up with a point estimator that comes with a good point estimate, but trying to make it into the one where you can quantify the uncertainty really well, that's yet another set of the research that you need to do. But in this case, we just train one model that's going to give us the entire thing. Just like this. We just train it with the stochastic gradient descent or its variance, and it just works. Well, I mean, this is a limitation but the limitation is all about our ability to produce the prior distribution. Sometimes that's very difficult, just like how it's difficult to come up with the new estimators. But once we actually come up with a prior distribution that reflects the problem that we want to use the estimators in the future, it becomes very systematic and then almost fully automated to find the new estimator. So then, of course, what is the next thing that everyone talks about when you talk to the statistician is that, about a third of them will tell you about the Bayesian statistics and the Bayesian inference. So we're like, okay, good idea. Let's think about the Bayesian predictive probability distribution. Feels like, in this LLM era, we don't really need the Bayesian statistics. I kind of agree, but also at the same time, it's just like mutual information, a fascinating quantity. So instead of thinking about it as, well, can I actually find a good model that's going to solve the new problems based on the data? Bayesian predictive probability or the Bayesian inference tells us that, we need to actually look at all possible models that are out there within our hypothesis set, and then we need to just marginalize them out. According to the posterior probability, there is a P of theta given D, there is a data set. This is a great idea. This makes sense because we don't want to commit to any one of these models because of the uncertainty. We want to essentially bake in the uncertainty or the handling of the uncertainty into computing this predictive probability. Super difficult. One thing that I am really sad about how we teach machine learning, in particular the probabilistic machine learning, is that we focus too much on Gaussian distributions to the point that we always say that, oh yeah, we can compute this. No, we can never compute it. And then the next thing we learn is that, oh yes, that's true, not everything is Gaussian. So what you need is that you need to find a conjugate prior that's going to work with your likelihood. I was like, but okay, so how do I find a conjugate prior that makes sense? Because I thought the prior is something that I decide, but somehow I need to decide the prior based on the likelihood. Something feels off. So when we are actually sticking to the truly, let's say, subjective Bayesian, let's say, paradigm, this is kind of impossible to compute. So what do people do? People usually use, let's say, MCMC, such as a Hamiltonian Monte Carlo or any of the latest variants, or people can use a variational inference. Some people use expectation propagation. I don't think anybody actually talks about EP anymore, but let's say we use a VI to approximate the posterior distribution. And then once we approximate the posterior distribution, or we can use a Laplace, we sample up from that approximated posterior distribution and then compute the average of the likelihood. Okay, sounds good. But this is really, really weird because why do we have to approximate the posterior? In fact, what we want is that we just want to get this number. This is, in fact, a single number. But here, what we're trying to do is that we're trying to actually get the distribution over the modal space, which arguably, I'm going to say, that is much difficult than trying to get a probability assigned to a single output, which is going to be much lower dimensional than the parameters. But we do that because we got stuck with this idea of the generative modeling. We got stuck with the idea that how was the data generated? There was a prior. There was some distribution over the data points. We sample one, and then we're going to generate something. And then thereby, we need to estimate the posterior distribution first, and then using that to compute the predictive distribution. But maybe not. as the prior, and then that's the idea behind the prior fitted network from the Miller et al. 2022 is that well, let's skip the whole thing. Why don't we directly train a neural net to take as input the data points and then the new input that we want to do the posterior inference on, just feed it into a transformer and then let it minimize this KO divergence, not at the posterior level, but at the predictive distribution level. It's really just training a neural network there, right? And then this is a figure from the PFN, and then this is exactly what they do. They sample the prior data sets based on their own prior over the distributions, and then using this set of samples to train a PFN, that's just a transformer. And then once you have a new parameters, you just do the feed forward, and then you get the answer. And it turned out that it works actually really, really well. This is the plot from the prior data fitted network. And then what you see is that these were the examples that were given. And then because this was a setup where the GP was exact, you cannot actually see the two curves here, right? There is actually a green curve and then blue curve. Green is from Gaussian process, and then blue is from the PFN. You cannot see the difference because PFN actually captured the exact Bayesian the posterior distribution perfectly. Even the confidence interval, so 95% confidence interval, overlaps perfectly with the GP confidence interval, which is exact in this particular case. This is very cool. It really works well. It gives us the efficiency as well as the effectiveness. And in particular, it works really, really well when the distributions are non-trivial. When you compare against, let's say, variational inference as well as the MCMC, like the no U-turn sampler that people are using by default these days. But then, of course, we noticed one thing is that, but this is not really satisfying because where the hell did the prior go, right? Prior was something that we could actually put our subjective, let's say, knowledge into, but the prior was done, decided implicitly based on our prior over the prior distribution. And then setting a prior over the prior distribution is a bit difficult. So we decided that, well, can we actually do a full Bayesian where we can be fully subjective Bayesian, we provide a prior as well as a likelihood all together. And then we do so following the prior fitting network like almost perfectly, except for the fact that we provide the additional tasks that share the prior with the target task. Thereby, we are asking the transformer to figure out what the prior that I have in my mind, and then use that information to perform the posterior inference, predictive inference, without having to go through the posterior inference. And I'll just go through it very, very quickly. It's very simple. You just make everything into the string, right? And then feed it into the transformer. Everything except for the problem setup is now all automated and then made into a systematic procedure, which is a really nice thing. Before, if we were not doing this, I would have to spend about 2 hours talking about this slide. But now I can absolutely tell you that, yes, you just make this kind of string and then feed it into a transformer and then train a model, and then that's it. So, and then what you see is that it actually just works. Again, it's a really interesting thing. This transformer is able to look at related tasks, extract out the shared prior information, and use the shared prior information in order to perform a different types of the predictive inference, given the target task as well. And then it all does it without spending any time. And then what that means is that I'll show you here, actually. Oops. I'll show you here. So we can make all those complicated things, again, using normalizing flow. And then that's also another advantage. We don't really care about the actual form of the prior, thereby we can use whatever we want. Unlike variational inference or the MCMC, where it's important to actually know about the precise form of the prior or whatnot. Otherwise, you do always get a bias estimate. And then what you see here is that in order for this problem, this particular set of problem to be solved, stochastic variation inference with a hierarchical prior, I think that we can do better. That's what Rajesh tells me always. It takes a long time to converge. And then this is a wall clock time. It takes more than 1,000 seconds. It's a very simple problem. MCMC with the hierarchical prior also takes quite a long time. In fact, takes more than 100 seconds, if not almost, I say 500 seconds. But then this neural net that we have trained, the transformer, looking at the exactly same amount of the information, takes less than 1/100th of the second, telling us that it is solving a problem in a very different ways. It's not doing a posterior inference, it's just directly doing a predictive inference, and it's able to actually solve this problem in a way that is very different from how we think the problem should be solved. So What that means is that there is a kind of repeated message that I want to send here is that the inference or the estimation, slightly different, but let's say this, I'll just use the inference for now, does not have to be about the generative process. I think that that's one thing that Mike Jordan and then Chris Bishop kind of, let's say, fooled us a bit for the past 20 years or so in the educational side, is that we need to think about the nice generative story. And then based on that one, we need the inference is all about essentially inverting the procedure. But I don't think that's necessarily the case. Looking at some of the examples that I just showed you, in fact, that's the opposite of the case. Depending on what we want to know, we probably can always find a shortcut solutions that are as good, if not better, than trying to invert the whole, let's say, generative, let's say, process. And then this Bayesian predictive inference is really the example that there is a case. We could skip the whole posterior inference step and still get the predictive distribution that tends to work better than using MCMC, which is, yes, high variance, but unbiased approach to the Bayesian predictive inference. And then this really helps us in a sense that it really allows us to question the way of the thinking in statistics that has been here ever since the beginning of the 20th century, right? When Fisher and Pearson were trying to say that, well, these are the things that we need to do. Because they never had fast computers, fast pseudo-random number generators, and then good optimizers. And once we have all those things are changing very rapidly. I'll give you another example. This is on a causal inference. Causal inference is something that fascinates a lot of people, including myself, because eventually causality is something that we need in order to intervene in the world. If you just want to make a prediction on the world, forecasting of the future, that's fine. It doesn't have to be causal. But causality is needed if you want to actually intervene and then change the world or to change how the outcome is going to be. It's super difficult. Even when we know that we know the target underlying structural causal model, so how the variables are connected to each other, and then what are the variables that we are interested in knowing, and then what are the variables that we can intervene on, we often don't know, in fact, how to estimate this causal effect of the action on the outcome. It's really difficult. For every single problem, you need to come up with some, let's say, bespoke, let's say, inference algorithm, or existing inference algorithms tends to have a too high a variance to be useful or require a strict set of the assumptions to be satisfied that we cannot actually check. But then you see where I'm getting it, right? We can actually do the exactly same thing in a black box manner. We start with defining a prior over the distributions over the structural causal models. And then we're going to draw a single structural causal model, and then sample from those from that particular SCM, and then using the Monte Carlo method, because these are all synthetic, we just generate a lot of samples to estimate the causal effect in an unbiased manner, and then use that as a target for this estimator that takes as input the sample data set with the extra information, such as whether the variables are intervened or not. And we just minimize the mean square error or minimize the pinball loss that is used for the quantile regression. So, okay. We can write some math as well. I mean, I'm not against mathematics. So if you're trying to minimize this mean square error, in the case of the causal inference, we actually end up with 4 terms. We can decompose into 4 terms. The first term is a Monte Carlo error, in a sense that the causal effects often cannot be derived analytically, even if we know the full structural causal model. But if you can sample from it, we can always use a Monte Carlo method to estimate without any bias what the quantity is going to be. But then, of course, for each of the samples, we have the deviation from the true one. So that's the one error. We can actually minimize this further by sampling more and more during the training time. The second one is a model error from the optimal predictor. So maybe the model is just not good and it cannot actually estimate the optimal estimate given the n many samples. So that's the error. Now, this one, we can also minimize it further. How we do that? We're going to just make a model larger and larger. That's the kind of let's say, idea behind the scaling up. And then let's go to the D. There's a finite sample error of the optimal predictor. Now, so when we have the optimal predictor, prediction or the estimate, given the finite number of samples and many samples, that may not be actually a good estimate of the optimal predictor when we had the infinite number of samples. So that's the D. Now, this one, we can also make it work better, although this cannot be actually minimized fully because in reality, we always work with a finite number of samples. And then this is an interesting thing. It's an identification error. Because sometimes, even with an infinitely large number of samples, we cannot actually recover the true causal effect. And that's the reason why we often have to run the randomized controlled trials instead of going to the electronic health records and then extract out all those data points. So that one, we cannot really do much about it. However, we can always minimize these three terms by minimizing the mean square error. And then if the identification error wasn't there, if the whole thing was identifiable, then we can find the best estimator that works with any number of samples that are finite. But that was enough of the math. The answer, and then does it work well? It really works amazingly well. It can actually find you all those estimators that are as good as, if not better, than the very standard estimators that people are using. So for instance, if you have a confounder, what is a regular thing to do is that you're going to fit MLP or linear regression, and then simply ignore the fact that this edge exists. Not a great idea, but still you can do that. Instrument variable, if I have an instrument variable, I'm going to use a two-stage least squares to to nullify this effect of the confounders. And then in the case of the proxy, we can do the proxy two-stage least square the methods. Sure, all fine. But then it turned out just a black box causal inference can find an estimator that has a much higher correlation against the true causal effect. And of course, I'll skip this one. This is not that important, although I think there some interesting things can be looked at. And then this is one example that is, I think, is very interesting, is that we often don't know when the setting is slightly off the standard setting, what kind of estimator we need to use. And one example is when we have a confounder and the instrument variable, both of them. Usually when we have an instrument variable, we introduce the instrument variable because if we don't observe the confounders. And then when we observe the confounders, we just ignore the instrument variable. But it's usually the case that you actually do get both of them. But what do people do in practice often is to actually ignore one of them and then go with the estimator, like two-stage least square for the instrument variable only, or just MLP for the confounder. But what if we give all of them to BBCI and then ask it to figure out an estimator? It turned out that you can actually figure out an estimator that works better than using either one of these available, let's say, extra information. And then this is really interesting because if somebody tell you that, okay, here are two estimators. One works really well with the instrument variables. The other one really works well with the confounders. Now trying to mix them together and then come up with a new estimator that's going to work really, really well, better than either of them, given both the confounders and instrument variables, it's really not that trivial. You have to actually think a lot. And then in my case, I thought about it a lot. I don't think I can come up with a solution at all. But this BBCI, which is a very automated procedure, was able to find this estimator automatically without me having to actually come up with any algorithm myself. And one of the issue with the causal inference is that we don't really have a true, let's say, a real world benchmark. There is one that is kind of real. We can use it. That is based on the impact of the job training program in US that actually went in effect early on at the end of the 70s. And then there were some programs that were run in a randomized manner. And then there were data that were collected from the states that actually did not run this job training program, so that we actually do have the observational and the randomized data as well. And then we thought, okay, let's use BBCI on this one. Can we actually recover the true causal effect of the job training program using the observational data? And it turned out that the answer is yes. In fact, we have all those confounders. So we'll say that, MLP and linear regression is the right thing to go about. However, BBCI always gets closer and it has a smaller variance compared to closer to the true value and then smaller variance compared to the other estimators. And what this actually, again, tells us is that given a true real computational constraints, we have to now rely on the advances that came out of the machine learning in order to find these algorithms, not ourselves, but by this systematic method. And then they will tend to give you a better answers than the answers that your own algorithms can give. Now, of course, there are always a question about the generalization. Will it generalize to the problems that are not strictly part of your training set? It turned out that sometimes yes, sometimes no. But the idea is that if your prior is as spread out as possible so that the real problem is going to be within the support of the prior, it seems like everything works actually perfectly fine. And then now we are actually in an era, everyone is actually looking at this kind of approach because people have noticed we can train these estimators in a systematic and nearly fully automated way. So there's a paper from the causal, titled the Causal PFN, Do PFN, and the BBCI is the one that I just presented. And what that means is that instead of thinking about the mathematical assumptions, let's think about the statistical process by which we can actually produce the samples that looks reasonably close to the real problem that we're going to solve. And then after that, the whole optimization procedure is going to take over and then give us the solution. And I tend to say that, well, the artisanal algorithm design era is almost done. We're now going to the industrialized era of algorithm design. Absolutely, you can continue to be an algorithm designer, and some of you will continue to be so, and very successful. Like the people who design and manufacture Bugatti in France, they make about 100 to 800 cars a year, and still make like $800 million because each and every car is very expensive. But there are only about 100 to 800 a year that is sold. However, ever since, let's say, Henry Ford, right, the early 20th century, like Ford, Hyundai, and all those companies like the Toyota sells 10 million cars a year. So because a lot of the actual manufacturing process has been automated. We focus on the design and sales, but not the actual construction or the manufacturing side. That part can be done systematically. And funny thing, this is usually one lesson that I have to remind myself again and again is that the best way to decide on what to work on is to read the papers by Leon Botou from about 15 years ago. Then after 5 years, you realize that, oh, this is a great idea. Let's work on that one. And realize that in fact, 10 years ago, Leon already worked on this. So this is a really nice paper, Discovering Causal Signals in Images. Unfortunately, this paper, they wanted to submit it to CVPR or some kind of computer vision conferences. The half of the paper, not really interesting, but the other half has this amazing idea that given two random variables, so set of the paired examples, can we tell what is the causal direction? Is it from XY or the Y to X? And then they turn it into a binary classification problem, and then it pretty much work. And then this is a kind of the simplified version of the causal discovery. If I have two variables, if I know that one of them is the action and then the other is the effect, how do I know which one is which? And it turned out that Leon, together with David Lopez Paz, who also worked on the quantile regression earlier, worked on it exactly 10 years ago because this paper went on archive in summer 2016. And then, yeah, it's a really nice paper to look at. So yeah, it's a true lesson. Go to the Google Scholar page of the Leon Botou, look at the papers he wrote between 2011 to 2016. I think that there are some gems there. So finally, I'm going to wrap up by talking about the identifiability because this is a question that inevitably always comes up. Whether you work on statistics, whether you work on the causal inference, or whether you work on machine learning, that is that how do you know that your algorithm or the procedure finds the right answer? It's a very obvious question for us because we're machine learning people. We know about all those cross-validation, held out set and whatnot. That's the best way to go about, by the way. But statisticians actually do care about it quite a lot. That is, if you have two separate observations of infinitely many samples from the model, this hypothetical model, if they actually coincide with each other, then the underlying parameters of the interest under this model have to also coincide with each other. Then we say that this hypothetical model is identifiable. And then we often refer to it as a mathematical identifiability because how we do it is that we set out with the set of the assumptions or the set of the axioms, and then we do the mathematical derivation to show that that relationship holds. But that's very super unsatisfying. Why is that? Because that really doesn't give us actionable, let's say, guidance on what we can do in order to find the better estimators, better inference algorithms in terms of the sample efficiency, in terms of the lower variance, lower bias, and so on. It just tells us that yes, the problem that you're trying to solve is identifiable. So what? So instead, we can now think about the computational identifiability. And then this idea only makes sense because we have now found this ability, or that we have the ability to systematically and often successfully search for an estimation algorithm in a computational manner. Instead of starting from the set of assumptions that describe what the model is, we're going to start by writing down the computational constraints that are imposed on us by the real world. And then we're going to add the prior over the problem space. And then we're going to decide the hypothesis space. Finally, we have to make decision about the search procedure that is the optimization algorithm. Now, fortunately, steps 2 and 3 are more or less standardized nowadays, right? So all we need to worry about is a prior over the problem space. And if over this prior, we could get 1 minus delta proportion of problems to be solved within the error tolerance of the epsilon by this found estimator, then we say that, well, this is computationally identifiable. So this is a definition. We have too many symbols, absolutely. You don't have to worry too much about the definition itself. But the idea is that somebody's going to give us the causal quantity of interest, because that's not the same thing that we decide. But often for the identifiability, you have to decide on that one and then say that this is the identifiable under that quantity, because otherwise we cannot really come up with a generic way of coming up with the notion of the identifiability in a mathematical way easily. And second, we define a prior over SCMs, combining both given and simulated distributions, because sometimes we will have some idea about some parts of the real problems or the problem that we want to solve. Step 3, define a hypothesis space reachable from an optimization algorithm. So it's a set of all possible estimators that our transformer can implement. Step 4, we're going to just run the optimization to search for the very best estimator within this hypothesis space. If that best estimator is accurate, that is that the error is going to be under epsilon, for most of the SCMs under the prior, that is at the 1 minus a delta proportion, then we declare it as identifiable under these computational constraints that we have decided. And then unlike mathematical identifiability, we actually can even get the posterior uncertainty over the identifiability itself. So we can say that, well, roughly it's going to be highly identifiable for the most of the problems, or it's going to be not identifiable for the most of the problems. And then that can be given to us as a number that is between 0 and 1. And then looking at this one, if the problem is more and more identifiable, given the error tolerance and the P of the identifiability, the curve is going to get closer and closer to the top left corner. And the less identifiable problems are going to have a curve that's going to get closer and closer to the bottom right corner. So I'll just give you one quick example where I thought was interesting, is that we often think that the more data is always better. That's true when we are trying to capture the correlations or the associations. However, when you do, let's say, individualized treatment defect estimation, it's very unclear whether more data should help, because more data could imply that due to the noise, a lot of the different individuals are going to look very similar to each other, this allowing us to distinguish across all those individuals and get the correct, let's say, individual treatment defect. And then according to the computational identifiability, we do see that, so conditional average treatment defect that is not individualized, more data always get us a better the correlation against the true, let's say, Kate, that is the conditional average treatment defect. But with the individual treatment defect, more data points does not necessarily lead to a better estimate, but actually gets a worse estimate. And then this kind of, let's say, insight is really difficult to get if you're thinking about the very sharp mathematical identifiability, because that's going to tell us yes or no. Here, we actually get an intuition behind the finite sample estimations as well. So essentially, we're now looking at we're trying to make the identifiability now actionable. So before, we made the designing of the estimator automated and systematic. Now we're actually turning the notion of the identifiability also as the automated, systematic, and thereby actionable as well. Now, of course, this notion doesn't have to be only about the causal inference or the causal discovery. It can actually be used for missing value imputation as well as a survival analysis, which will be a kind of, let's say, relatively quick, let's say, extension of this whole idea. And the funny thing is, another lesson is that the Rajesh Ranganath, who I worked together with, He wrote a dissertation titled The Black Box Variational Inference, Scalable Generic Bayesian Computation and Its Applications in 2017. And then in one of the chapters, she talked about this. Rather than choosing models based on the needs of the data, models get chosen based on the ease of deriving inference. That's the current practice. The need to derive inference creates some costs that hinder the rapid exploration of models. BBVI, so black box variational inference, allows practitioners to design, apply, and revise models of their data without painstaking derivations each time they adjust the model. This moves the generative probabilistic modeling process more towards building models for data rather than the models for inference, because models for inference may not actually be about data that we have to work with. And then this kind of automation and then systematic, let's say, approach to estimator design, as well as the identifiability the check, is going to allow us to focus on the actual data and the problem we want to solve. And then because we're in the 21st century and we are mostly the computer scientists, I think we have to push this philosophy further and further. And then we have to rely on the power of the learning. And that actually concludes my lecture. Then here's an awfully incomplete, let's say, reference list based on what that I based my lecture on. Thank you.
Amazing. We have time for a few questions, so okay.
Thank you for the amazing talk. I'm curious if anyone has tried any interpretability on these methods to try to understand what the model is actually doing.
No, just because these are very reason work in general. You can actually use any of these methods that have been proposed for the interpretability and explainability to these estimators that have been found. But I'm actually not sure whether that's actually going to have any reasonable, let's say, outcome that we would anticipate. We probably can get some sense of given a particular problem, locally, what are the things that this estimator does? We'll be able to probably figure that out, but nothing global. If we could, we wouldn't have actually done this. We would have written down the algorithm ourselves. That's my guess.
Thank you very much. On one slide, you have told about Ethereum, where you transform distribution by some maps to another variables, which would have the same mutual information. And I'm interested in what type of transformation have you been used to train your estimator? And for example, if I would use some diffusion-based models to transform this distribution, how then the network would generalize to the unknown one, which probably do not follow for the students and Gaussians.
Yeah, so in this case, we start from the Gaussian, almost always, doesn't have to, can start with the uniform as well, as long as we know how to compute the mutual information, and then we apply any invertible nonlinear transformation. And then you can actually have a lot of different things like the half cube mapping. And then we try to make the marginals bimodal, and then diffusion can be actually used there as well, because as long as you choose the diffusion map to be, the invertible, because not everything has to be invertible. But then one limitation that we have is that this whole procedure actually transforms individual random variable separately. So yes, this isn't actually universal in a sense that there could be a transformation that applies to both X and Y jointly. But then it's unclear how to choose a transformation that's going to maintain the mutual information. I think that there must be another way to do that, but we haven't really looked into it yet.
Hi, thank you for the talk, by the way. I was wondering that how can we 100% sure about the quantile regression part, that model outputs like upper quantile and lower quantile, and how can we be sure that upper quantile is always higher than the lower quantile? I mean, the model is not that deterministic, and I'm really curious about that.
You're absolutely correct in the sense that this Q here, the target quantile is going to go into the neural net that produces this theta hat. And then you're absolutely correct. There's no constraint that we put that makes the predicted quantile of the higher number to be actually higher than the predicted quantile of the lower quantile. But that's the amazing thing is that because we're working with a lot of the synthetic data, we can actually train the model with the nonstop continuously generated data, and it actually learns to do that pretty well. And then one of the reasons is because this pinball loss is such that if there is that kind of flip, although it's looking at one example at a time, that's going to actually penalize the flipped version dramatically to the point that near the end of the training, everything has to line up pretty much as we anticipate. Although we can always make it more explicit, but making things more explicit tends to have a worse outcome in terms of the optimization. So just let the transformer take care of a lot of things.
Any other questions?
Thank you for your talk. I like the part about mutual information estimation. And I was wondering if you ever considered doing in-context learning for mutual information estimation, similar to TAP PFN style.
It's pretty much same. It's pretty much same. So if you look at the ISAB, so it depends on how we encode it. So that's what I meant by at the very beginning about the representation. We can put it into it. But in the case of the mutual information itself, we know that the whole thing needs to be, or there should be permutation invariant. So thereby we actually use just we took it away from the Andreas Krauss group where they use the attention across a different axis. But you can absolutely do it with the PFN style, just encode it into a string, give it into a PFN, trying to make it predicted. That's absolutely fine. But you'll have to think a bit about the ordering effect, that how you're going to marginal out the effect of the ordering of the data points.
Can maybe have a question myself, which is, given that we're talking about statistics, how do you feel about the lack of guarantees of correctness in any of this? Like, does that even bother you on a philosophical level? To me, it just bothers me that I'm going to have this model where probably it's going to do a good job, but maybe it's not.
So you're absolutely correct. In fact, I'll just go to the identifiability for a second. So what we are doing, you're correct in the sense that we are relaxing the problem a bit. So if we have this epsilon driven to 0, and then delta driven to 0 as well, then we actually do recover the original mathematical identifiability. Because even in the case of the original design of the estimators, what we can even think of it as we're collectively doing a search, but it's a discrete search. We try one at a time, and then hopefully we get closer and closer to the solution that's going to have the 0 tolerance, and then the works for the any problem we have. But in order to work with a more computational, let's say, optimization algorithms, we need to relax it a bit by introducing epsilon and delta. It actually kind of connects to all those PEC learning as well as various the other notions in the mathematics that relies on the epsilon delta. And then we're using essentially that kind of framework in the context of the identifiability of these statistical quantities. So yes, am I comfortable with this relaxation? I mean, you know me, I'm very comfortable. However, I have noticed that not a lot of people are comfortable. And then perhaps there will be a way to refine this to make it even smoother, but that is going to be always getting better and better as we get closer and closer to a true thing.
Any other? Oh, yes.
Do you think we could do something similar by searching in code space or symbol space or some interpretable space?
Yeah, absolutely. In fact, let me see. Do I have it? Oh, maybe not. Maybe I don't have it. But essentially, one of the reasons why I think we are in a really exciting era of computer science and statistics and whatnot is because once we define this kind of criteria that are computationally motivated, and then we write down of the problem, the initial, the in between the implementation stage can be automated. So one of the things that you can imagine is that I'm going to go back to just 2 more slides. So let's say I am in this kind of situation, and then I'm going to use the black box causal inference to solve the problem. And then I don't know whether this is enough. Now I can plug in this computational identifiability as a criterion for, or the verification for the coding agents to figure out what more data needs to be collected. And then that is a very discrete choices. It's almost like writing a code to go out there and then collect more data or not, until the point at which we see that the computational identifiability is actually improving. So thereby I can stop and then start getting the estimator as well. So in that sense, yes, I think the coding agents are going to tell us what to collect the data and then how to set up the prior distribution. And then given that one, we're going to use a much more effective or the efficient, let's say, gradient-based optimization to find the estimator and then check if the estimator works well. If not, we actually repeat the procedure. Yes.
Any other questions? Okay, if not, we're gonna stop here. Let's thank our speaker again.
Thank you.
Kuyung is gonna be around until Wednesday, so if you have further questions, just bug him. And we're gonna go for lunch now. And then for the mentorship, everything else session, we'll come back to this room, and then from this room we'll like spread depending on what you want to do. But yeah, cool.
can I get a show of hands of people who have already loaded the collab? Okay, thank you. We'll wait just a little bit for other people to do so. Also, can I have the TAs come to the front of the class, please? Sorry, guys. Sorry? It's in general. This one in here. Okay. For those of you who don't know where the collab is, thank you. Just come. Okay, so welcome. I'm very excited to give this RL tutorial. I also gave an RL tutorial at EEML last year, and I really enjoyed it. I think RL is one of those topics that you learn and understand best if you're actually doing it. And I think everyone has Claude Code and in general LLMs at home, but only here you have TAs and a constrained amount of time in which you get things done. So they are really kind and really nice. They really want you to learn and to assist and guide you. So please don't be shy to use them. Thank you so much, TAs, for doing this hard work. Human learning, I'm actually working on education, on AI for education, but I think human learning is here for our best and to thrive and here to stay. So please make use of this resource. And thank you for the EEML organizers to still want to have TAs for the tutorials, because with the amount of people using LLMs to answer questions in tutorials, there's a chance that we might not have TAs forever in EEML. So please, use this resource. Thank you so much. Please move around the room, so distribute randomly so to be most accessible. Thank you so much. All right, so hope this is fine. I feel a bit of noise. Yeah. Okay. Okay, hope it's better. Okay, so welcome to this tutorial on RL. We have a lot to cover, but I think I'll go step by step, very clear, smooth, at your pace. We can go as slow as you want, so you actually understand the concepts. We also have a solution for people who are already familiar with RL to skip ahead, go to part 2, where the interesting stuff happens, the RL for LLMs. If you already feel confident in understanding how to implement a neural network policy and the return and so on, just go straight to part 2. But for the rest of the class, we are going to go step by step and try to understand what is RL in practice and slowly build towards PPO, GRPO, which are the learning algorithms used today in LLMs. I have to say, please go to the tutorial and start already running the cell that will download everything that you need. Especially connect, please, to the GPU if you can. But if not, a CPU will also do, so that you can already start downloading the import utils and everything else. And especially for the LLM part, we will work with Qwen, 500 million parameter model. Please make sure to download that at the beginning while I'm talking. All right. Okay, so as I said, well, maybe just an intro of myself. I'm Miruna. I'm a research engineer at Google DeepMind. I'm from Romania. I've done my studies in the UK and then got an offer from DeepMind in Paris. So I've been for 7 years now in Paris working on RL, NLP, LLMs. Now for 2 years, I've worked on education. Like we're trying to improve Gemini for learning, for teaching. If you're interested in that, please grab me. I'll be here for the full week. I'm doing this tutorial with Sieva in the other room. He put a lot of work into this tutorial, actually, the part 2 especially, and the teaching assistants. Thank you again. Okay, so the goal for today in this tutorial is to implement RL algorithms and then use them to align a language model, a small one. We'll have to do a couple of assumptions about the language model to be able to train it with the resources that we have in 2 hours and the internet and Colab. But hopefully we'll manage to get there. So in the first part of the tutorial, we'll build a policy gradient agent from scratch. You've already seen the policy gradient algorithm in Andrea's talk, but I will explain again. And then in the second part, so in the first part, we're just going to work in a grid environment. The second part, we're building on this reinforce algorithm to PPO and to fine-tuning an LLM. I will explain the components and you'll have time, we'll code together. I'm having a collab up. I'll give you time, then I'll start coding at the end of your time and we can build the solution. You can see the solution live, hopefully, if we have time. Okay, so for the basics, reinforcement learning is about making decisions through experience. An agent will perform an action. The environment, which is where the agent lives, will respond with a reward. And the agent will adjust its behavior based on the reward that the environment gave back. And this is then repeated, and it's called experience. So RL is a form of trial and error learning. Okay, so the environment in which we will work is called cliff walking. It's a grid environment, so you can see the goal of the game is for the elf, you see, to go from the chair to the cookie. And there's a cliff in between. All the brown part is where the agent will fall and the episode will end with zero reward, like with a big negative reward. The goal of the agent is to follow the green path somehow and then get to the cookie. So to achieve this, okay, so maybe just to define some more terms. The elf is the agent. The agent is taking actions in the environment, as we've seen. Up, down, right, and left. 4 actions from 0, 1, 2, 3. Every action has this one integer associated with it. So if the agent first has to go from the chair to the cookie, what does it have to do first? Up. So action 0. And then so on, can do anything. The environment is giving you the reward. This is something that we will not have in LLMs, but the environment is giving you the reward. Every time you take an action, the environment will respond with an integer, which is -1 every time you step on the green, -100 if you step on the brown, because that's when you fall into the cliff, and 0 when you get to the cookie. So that's the reward. That's the agent, you know, the environment. But now there's one other term, the state. The state is also represented as an integer. A state here is very easy to see because it's a grid of 4 rows and I think 13 columns. No, 12 columns. Then it's a 4 by 12 grid. So every state is just a pair of integers. So the agent is starting at position at state. Someone shout 30, yes. And this will be encoded as an integer, which is just like, I can just tell you, it's like the number of rows, 3 multiplied by 12 plus the column. So you have it in the collab somewhere. Yeah, okay. Now, the agent will take these actions in this grid until it gets to the cookie. So, I mean, hopefully that's the goal, to get to the cookie, and we'll train an algorithm for the agent to achieve that. And who decides what actions the agent takes? That's the policy. The policy is like the brain inside the agent. It's like determining which action the agent takes in a given state. So if the agent is, I don't know, in the position, in the starting state, in the initial state, hopefully the best policy that we could learn will tell it, go up, as we've decided that this is the best solution. But it's the policy that determines the distribution over actions conditioned on the state. Actually, this is not a deterministic agent. It's like having a distribution over actions. Okay, so the policy is actually the most important concept in RL. It's the thing that the RL algorithm has to learn. Okay. Now, every time the agent takes an action, the environment responds with 2 things. As we said, the reward, but also a new state. A new state is like the new position that the agent is in on the grid. So very intuitive, I hope, very easy. Right now, like maybe it's confusing, but the reward is negative. That means it's called a penalty. And the goal is to minimize the penalty or to maximize the reward, their equivalent, that the agent will take from beginning to the goal, to the cookie, from the chair to the cookie. So can someone please tell me, what is the maximum total reward that the agent can get from the chair to the cookie? Minus 13, yes. It has to go once up and then 12 rows to the right. And then I said, when I go to the cookie, it's reward 0. So it's minus 13. Is this clear for everyone? Yes. The shortest path is not 13. That's what you're asking? I don't quite understand. Yes. Yes, you're very close to the cliff. So when you fall into the cliff, you have a reward of minus 100, which means you're not maximizing the reward or minimizing the penalty. So the episode ends, the game ends when you fall into the cliff, and you start again from the chair. Yeah. Yes, that's true. Yes. Okay, so final 2 concepts before we dive into. So there's a time step and an episode. A time step is a single step in this environment. It's an agent environment interaction. One time, that's a time step. One action. One action to which the environment gives a reward and the new state. That's one time step. Okay. Now, several time steps until the episode, until you fall off the cliff or get to the cookie, that's an episode. So it's a full sequence of time steps from the beginning, the initial state, and every game, every environment will have coded an initial state or a set of initial states. So that's given as part of the environment. And then the episode ends whenever, again, the environment decides that the episode ends, which is here, either you fall off the cliff or you reach the cookie. So unrolling an episode, this is also a term that is very, very frequently used. What does it mean to unroll an agent or an environment? Unrolling an episode in this case, it's just letting the agent take actions until you finish an episode. That's all it means. Like, it's also called a trajectory. People use all kinds of terms to refer to this, but unrolling, it just means starting from somewhere on this grid and letting the agent play actions, whatever the policy decides those actions are, until the episode ends. That means unrolling. Okay, so if it's your first time learning about RL, maybe these are already a lot of concepts. I also have to say, RL is not easy. Like, when I first heard of RL and started doing courses in RL, I didn't understand anything. I had to listen to it again and again. And then at some point you understand and it clicks. But if this is the first time, it will be tough. If this is like already your 5th time that you're hearing this, probably you're already a bit bored. But sorry, you have to go with the pace of everyone. So again, but RL is not easy. Just bear with it. And at some point it will click. Just give it a chance every time you hear about it. So, okay. The reward, the policy, and then the learning algorithm. This is what the agent improves with an update. We'll talk more about the learning algorithm in a bit. But first, let's talk about the reward. So we will implement together the key pieces of the reward. So just a few lines of code to implement it. You've seen this formula already in this morning. The way you accumulate reward, as I said, like every time you take a step, you get a reward from the environment, and you want to optimize for the goal, which is reaching the cookie. So there is a formula to discount steps in the future with this gamma factor. Gamma is the discount factor. So if I'm here and I take this, and so on, if you can see my cursor, then here, I'll put it here. So if I'm just moving through this environment, every time I'll receive a reward, and every time step, like if I need to calculate what is called the return, which is the sum of rewards from this point, this state, until the end of the episode. And every time I'm taking a step in the future, a reward in the future is also going to be discounted by this gamma factor. So this is the formula. And I guess the objective of the agent is to maximize, to get the most reward, maximize the reward. So the sum of rewards over the whole episode, if gamma is 1, you just have, the sum of all the rewards in that episode. But you want to discount future rewards because the rewards in this moment in time, in this state, matter more for you than those in the future. So to account for this fact that immediate rewards are more important, we have this gamma factor. And you can see the formula to expressing it. Here it is. I can even zoom in. Really written out, spelled out more concretely. So every time step, you can think of it also recursively, because this is the thing that you will have to implement in a minute. The easiest way is to just think of it recursively, as I said. The return at time step t is your reward at this time step plus gamma multiplied by the return at time step t plus 1. So at the end of the episode, when you are just here, you see, if you would be here with your agent, and you take whatever reward you're taking in that state, that is your return, because there's no other steps until the end of the episode. And now if you go one step backwards, let's say you were here, you were in this state, the return from that point, from that state to the end, will be whatever reward you get to get here, that's -1, plus gamma times the return that you got at this step. So I don't know if you can think of it as well recursively in your head. but try now to think of it yourself and implement it in here. You have a raise not implemented error. That's the bit that you have to delete and write your code there. There's some instructions and like, I'll just be quiet for 5 minutes and let you code it, unless you have questions. So maybe a thing that I haven't specified. So the return, you can calculate it for every state. So that's why I said like the return in the last state is just the reward of the last state. But you can calculate the return for all the path in like for every state in the episode. So who does need more time, or could we go into the solution? Who needs more time, put their hand up. Or like, okay, who's done, put their hand up. Okay. 1 more minute. Yes. Okay, let's go to the solution. So can everyone see here? So we have a function, get returns, so that's passing this gamma function, gamma parameter. It's really a parameter that you, as an engineer, you would choose. 1, from 0 to 1, like 1, 0.99, 0.98. That's a typical one. Or if your environment is like really like you want to like you only want to account for more recent rewards, you would put it like 0.1. That's very extreme. Like in practice, 0.98, let's say. So gamma given. Rewards. This is the rewards that your environment has given from initial state to your last state. So it's a list of floats. Cool. So now you want to have the return, to implement the returns, calculate the returns for every single step in your episode. So what do you want to do? I said the easiest is to think recursively, starting from the end and working backwards. So for your reward in your list of rewards, and you want to do this in reverse order, what do you want to do? You want to calculate the current return, the current discounted return. Okay, is your current reward plus gamma times, well, I just look at the formula, times what? Like I'm just thinking, like it's the return at the previous time step. So it's the discounted return, current discounted return. It's 0 right now just because I said at the last state, the current return is just the reward. But then if I think of the next step, so reward at time t. Well, I hope it's just clear from the formula. The discounted return at time t minus 1 is the reward at that time step, plus gamma times the discounted return at the previous time step. And then you want to add that to the list of returns, insert at position 0. What did I do? Insert at position 0, what? The discounted return at t minus 1. And then the discounted return at time t will become discounted return at t minus 1. I hope this makes sense. And then you can just see if I did anything incorrectly. Okay. So that's your return. This is the quantity you will maximize later in your learning algorithm. Okay, so if you have the return, now let's move on to the policy. So in your, the policy, as I said, is the brain of the agent. It's denoted by pi. And it really is, as I said, like a distribution over the actions that are possible. We have 4 possible actions, so we want a distribution over the 4. Why a distribution and not a deterministic mapping? Because we need the agent to explore. The agent doesn't know. The actions are random at the beginning. So the agent needs to explore, is in this environment better to turn first up or right or left or down? Initially, it has to start with a distribution of like 0.25 for each of those states, for each of those actions for that state. So we sample from this distribution, and the agent will sometimes, take an action that will give it very badly fail the episode, but otherwise it will be successful. So that's exactly why we need a distribution over the actions. So what we actually do in practice is we have this action scores, compute the logits from it, we convert them to probabilities, then we sample from that distribution to get what the next action is. This is effectively like a random policy. So if we are to implement now our first policy, a tabular policy, let's move to the implementation directly. So you have a grid policy, meaning you want to initialize parameterizable function that it's exactly number of states. It's like number of rows times number of columns So it's better just to write it. Self-policy is, we're using Torch, so I hope. Okay, we want to initialize a parameter that is just, let's say, zeros over number of states, number of actions. And then this is my policy, it's just a grid. And then you would initialize this policy given the observation that you see. And those will be your logits. That then, those logits, you will pass them to a categorical distribution. That's your distribution over the possible states actions. That's your action distribution. Then you get the probability and you sample. That's your sampled action. Sorry, I forgot to run this. What did I do? Oh, I forgot to run one cell. But if you implement it, you can already see it. Oh, no. Oh. Yeah, okay, let's see. Oh. Okay. Yes. Thank you. So you could run this several times and then you will get a different sampled actions because you can see your probabilities is just a uniform. And then when you sample an action, a random action, this is basically the most basic implementation of a grid policy. And you can see this is completely random. The agent will fall off the cliff. You can compare yours to your neighbors and so on. And the idea would be now, based on this implementation, what algorithm can we add on top of this? Like what is the update algorithm that we can add on top of this policy implementation to make the agent be a bit more smarter than just random? So this algorithm is called reinforce. So the intuition is that if a trajectory had a high return, so if we have an episode and at the end of it we observe the total return and it had a high return, we will increase the probability of the actions taken in that trajectory, all of them. And if it had a low return, we decrease their probability. So we're reinforcing good behaviors. This is where the name of the algorithm comes from. So the objective function is to maximize the expected, can you see the expected return of that trajectory? And, like, how do we do this? We just want to maximize this function. We use gradient ascent because we want to maximize it. So this is how we calculate the gradient of the objective, very similar to supervised learning, you would say. But as Andrea showed in the lecture, there's a lot of math beneath. I don't want to hide it to you. There's a lot of math beneath to arrive at the log trick, which is expressing this, which is the reward is not differentiable. So how do you get to estimate this? You have to go through quite a lot of math. Like if you look through, I don't even want to decollapse it because it will be intimidating. But for math, if you're interested in this, you just go home and with a paper and pen, you try to solve it and understand the log trick yourself. There's no point in doing it in a tutorial. So instead, you just have to trust me that the objective, our initial objective, can also be expressed with this logarithm, a logarithm of the probability of the actions given the current state, all summed and weighted by the return. You can take it like, this is the loss function that reinforce is maximizing, it's trying to update. So there is some math behind it. Again, it feels like I've just had a magic wand and like put you this formula. But there's no point in going through the math now. Instead, if we focus on the expression of the loss, we can try to break it down. So first, the derivative with respect to the parameters of log pi action given state. This is the gradient of log probability of the action. Before we had this categorical distribution, we sample an action. That's the action. You can then get the log prob of it. That's the quantity that, probability that you can get from the implementation, given your distribution. This tells us in which direction in the parameter space would that action be more likely. Now, GIT, as we've said, is just that we've just implemented it, is the discounted return for time step T in episode I. You just implemented it earlier. And then we simply scale the direction, this log, the gradient of the log probability by the return. This is the whole point. Like you scale the actions that you took in that episode, you scale them by the return. So if there's a large positive return, it will mean that you make all the actions more likely. If there's a negative return, or like this flips the direction of the gradient and makes the actions less likely. And then we average this over all steps and all episodes in your batch. Yeah, so this is the loss that you will code now. If you can take like 5 minutes to read through the text, and then here, there's an exercise, implement the reinforced loss. You have the loss written again here, you see? Just follow the terms, think about what each term means, and try to put it into code right here, calculate reinforced loss. So should we give it a go to the solution? Or you need more time to think? Who needs more time? Cool. Okay, let's try to maybe you can finalize your solution as I'm writing it. So we want to, so the agent is like the body that has a brain, this policy. We pass the untrained policy, but the agent also contains this update algorithm. So the update algorithm, so we'll do this, we'll get the logits, as I said, from the policy. The policy right now is just a grid. We'll get the state as you've seen in the past. Distribution, categorical, we'll sample an action. We'll get the log probability in this way, sorry. We'll get the log probability. Then we'll pass the action and this log probability somewhere in the update function. But the update, so the update function just collects in batches, just playing the batches of rewards and log probabilities collected from episodes. Like you unroll the agent for hundreds of times to have many episodes. And then you have the log probability, and you want to calculate the loss based on the rewards and the log probability. And this was the task. How do you calculate the reinforced loss? Well, you have the episode rewards. You need a return. Not a good idea to call it return. Episode return from the episode rewards. Well, you know how to get this. You get rewards, I think, gamma, and what was it? Rewards. This is how you get your returns from your own function. And then you want to calculate the loss. Okay. The loss is this. So you want the log probability weighted by the return. Well, the log probabilities are this ones, weighted by episode returns, let's call them. Okay, but you want to do an average over them, a sum over them, actually. So you use torch sum, and you want to maximize the reward, but PyTorch is doing gradient descent, but you want gradient ascent. So what would you do? You just put a minus here and transform a minimization problem into a maximization one. How was that called? Get returns. Yeah. Thank you. Yes. So nice. I should just let one of you code actually this. Okay, so it passes. I hope this makes sense. Now, we want to put this in action. Like now we want to train the agent. You can actually look at this function, train agent. So we collect batches of experience, as I said, action, probability. We put them, this environment step given an action will give us the next step, the reward, and so on. There's a shaped reward. I haven't talked about this. If you are intrigued by this, that means you know a bit of RL already, can come talk to me after. It's for practical reasons to advance a bit this tutorial that we've added a shaped reward. And then you collect this average reward means and so on. And then this is actually where things happen. You have to set the learning rate, gamma, and so on to train the agent. And then we wait a little bit. And then we'll see the loss, how the agent is, no, the loss, the loss is the reward. And then hopefully converging. And then we'll see how this reinforced agent in a grid with the grid policy is doing. Yeah, so hopefully this will not take a lot of time, depending on the internet. And perhaps as the agent is training, I can talk about, okay, we have the learning algorithm and we have a grid policy, but the policy is like, as I said, the brain, the thing that we use to sample actions and to get actions. So we could swap that with a neural network policy. And nowadays, all major agents are using as their policy a neural network. We just use a grid policy, but we could swap it with a neural network one. So let's say here it was a grid environment, so it makes sense to use a grid policy. But if you would have something like images, you would want to process them with an embedding and few layers and so on. So just for demonstration purposes, I think we could do that exercise. Okay, it's still training. I don't know. Has it finished for anyone? Good. Nice. So for the neural network policy, can you see how it's defined? You want to define an embedding and a policy net as a few layers. So embedding, do I remember my PyTorch? That's the question. I think it's NN embedding. And then you need to have the number of states because that's your input size. And then let's say 32. And then for the policy net, you want to have, let's say, a sequence of layers. Sequential. And then you would have to have ReLU layer, ReLU layer. And then can someone tell me who's following this neural network policy? What will have to be the last linear layer dimension? Yeah. And so I wouldn't check this yet, but so you would apply the embedding to your observation, then you get the action logits, and that's your policy that you can just swap the grid policy for. So you replace the grid policy with this neural network policy, and ideally you should have even better performance. Let's look first First, let's run this. And because this will also take some time to run. And then let's check what happened in the other case. So you can see that it's approaching 0. Now, what is the agent actually doing? That's the interesting part. Can everyone see the screen? So it didn't take the most efficient path. Look, even like how many loops it's doing. But it gets to the cookie. You probably have a different solution. Have you seen this video, like of the grid policy trained with reinforce? Do you have something similar? Is anyone has anyone gotten, like, have you been able to get this video? Okay, has anyone been able to train a policy that gets the optimal solution, like the agent not taking any loop? No, okay. Well, let's see if the neural network is able to do it. It's very slow. Yes, so the embedding dimension has to go from number of states to something else, to a dimension. 32, it was just vibes from me. It could be something else, 64. Yeah, I think yeah, you could choose actually here to play with another policy net. This is not a set in stone solution. This is just an example. Okay. It's still training for me. Did anyone manage to train the neural network policy? Yeah. Cool. Is it getting to the optimal solution? No. Just put more layers. Okay. Okay, interesting. So this was mine. Oh, almost there. Can you see? It's still deciding to do an inefficiency at the end. I think if I would let it train for 700 steps, it's usually getting the FIME solution. So under 200, there's a lot of randomness in this because the agent is exploring. So that's the whole point. And then you reinforce all actions that you have taken, depending on what actions you have explored in the beginning. You're reinforcing all actions that got into, a better reward. Let's say in the beginning, your reward was minus 200. When it got to minus 100, all those actions got reinforced according to the return. So here, the reward is probably something like minus 17, minus 18, I don't know. And then that's probably the best this agent could do in the amount of steps that I've given it. You could increase the number of steps in the parameters here. You could play with the learning rate, the gamma, and so on. Like all these hyperparameters, I've actually had to carefully tweak for you before this tutorial. Don't imagine that actually a lot of the RL work is in finding these hyperparameters that actually make the RL algorithm work. Okay, you probably all have gotten a different solution. If you're interested in this was mostly to demonstrate a few points. One is the way you choose to implement the reward matters. Two, policy is something that you can implement in very different ways. It can be a grid policy. You can have a neural network policy that you implement in whatever way you want. And the policy is part, but not the learning algorithm. The learning algorithm is still part of the agent, but it's separate from the policy. The policy is the one that chooses actions. The learning algorithm tells you how do you optimize those actions. So that's the end of part one. I think it roughly took us an hour, which is what I mostly expected. This is just the intro to RL. You have now seen reinforce in action. Now we're ready to take a few more steps in complexity to get to PPO, which is reinforce on steroids, to put it into training an LLM. But just to recap, so it took us 300 steps to teach an elf to walk across the grid to get a cookie. Now imagine that you have an action space of like 200,000 tokens and an episode much longer. We will need a more complex algorithm to make and like this elf didn't even learn well, right? So how to say, the RL algorithms will have to be more complex. So we'll try to look into PPO and then move to GRPO. If these acronyms don't mean anything to you, I hope they will be a bit more familiar and will help you, because like sometimes even in machine learning interviews, they will come up. So, okay. Moving on to LLMs. Okay. We will use Quen 2.5. This is a 0.5 billion, so like 500 million parameter model. It's small, but it's all we could fit on a collab. It will be, you know, decent, but don't expect to do this collab now on LLMs for performance, but rather to be instructive, hopefully. So as I said, PPO, GRPO, DPO, I don't think we'll get into it given the time. But so we've seen RL in this grid world environment. How does it translate to the LLM world? We all know that ChatGPT, when it came out, they managed to make PPO work for LLMs, and that was like with RLHF, with reinforcement learning from human feedback, which was something that, you know, other labs took a long time to replicate the same results. And so why is that? How is that? That has become, since ChatGPT, part of the recipe for training any LLM. So it's not on the collab, but just to give a bit of background for people, there are two phases in LLM training. There's the pre-training, where you essentially just do next token prediction. You have the full internet of data, and you just want to predict the next token in whatever huge documents and all this internet data that you have. So you have batches of examples filled up to the last sequence token. And you just want to predict the next token. This is essentially training your model, the representations, what language is, how language works in general, but it's not doing anything useful. So you need the second phase called post-training. And in post-training, you have two steps. First step, you do instruction tuning. You make your language model a bit more useful, in the sense of like you give questions and answers, and as your data set. So the prompts, and then what the model should respond. You train your model to be useful in that sense, but it's mimicking data. You have data sets also, like the examples are not filled to the sequence limit. You have this prompt, and you want to predict not the prompt, but just the response. Instruction tuning is helping your LLM from just knowing language to also knowing how to respond to queries. So that's a step called supervised fine-tuning. We'll not talk about it, there's no RL in it, but it's learning, it's teaching this LLM to mimic responses, to have a certain format. But then the next step, which is a lot more difficult to nail, is the RL part in it, which is RL fine-tuning. And it has a lot of forms, this RL fine-tuning, in which you align whatever you've had before, this LLM that was instruction tuned, this LLM that knows how to respond to queries. You make it also preferable to humans. You make it so that the style and the tone in which it's responding, it's pleasant to you will like seeing it, basically. Or it's correct. It moves the hyperparameter space of the base model into a more likely direction. Okay. So we're going in that second phase, second step of post-training, which is RL fine-tuning. So when we were talking about RL before, we said the environment is giving rewards. Here, the environment, there's no environment to give us rewards. We have an LLM that gives responses. So we will need ourselves as engineers, researchers, to define what the reward function is. And there's no limit to this. It depends on your context and your application. So your reward function can be something as simple as a reward function is just taking the state, whatever that state is. In the case of, a grid world, it was just the pair of row column. Now, in the case of LLMs, the state is your prompt, is the thing that you want to have an answer to. So given the state, you want to have a mapping from that state, that query, to a scalar, a number. So whatever crosses your mind, depending on your application, there's no bad reward function if it fulfills your needs. So an example of a reward function, just make this state less than 10 words. It's a valid, if the response has 10 tokens, then reward 1. If it has less than zero tokens or more than 10 tokens, reward 0. Another reward function, if your response contains a certain word, just reject it. Like you could think of a lot of type of reward functions. Sorry, did I say that the state is the state that, is the prompt, and then the reward will score the action. The action is the fully generated response. Okay, so another reward is, let's say, was this correct or not? And you have a form of like correction verification. For instance, your response is code, and you would want to check, is that code compiling? Then reward 1. Is it partially compiling? Reward 0.5. Is it not compiling? Reward 0. So you, as an engineer, define what this reward function is and how it looks like. One other type of reward, more abstract, use an LLM as a judge to output a number based on, let's say, is the sentiment of this response positive or neutral? Then again, and you give a reward based on that. So you can fabricate those rewards. RLHF, yes. A very good question. So the question was, when is the model rewarded? Is it after every token or after every response? And there's no easy response to that, it depends on the algorithm. So for instance, PPO that we will talk about, I think you operate at the token level, but GRPO, which is the one for DeepSeek, it's at the response level. I think the reward, usually you would want it for the full outcome, which is the full response. As a rule of thumb, I think you could better think of like full response. And then you can further make it more granular for PPO especially. Like I think the reward is always for the full response, but what you perceive as an action, is it a token or the full response, differs based on the algorithm. I think that's the correct answer, sorry. Okay. So if you look at like before we had this agent environment state reward, for the language model, you have several tokens. That's your prompt. That's your state. So the state in LLMs is the full prompt that you want to give it. Then the response that the LLM gets out, the full response, especially in GRPO, that's the action that the agent takes. So it's like a bandit. If you know bandits, it's like a bandit. And then that response we need to score with our reward function. Now, I haven't finished with saying that reward functions, you can define them very simply. As I said, if it's more than 10 tokens, give reward 1. But you can also make it very complex. And actually, the reward function is very, very important for how you train RL for LLMs. RL for human feedback, what does it mean? Well, you have humans see different 2 responses for the same prompt, and they will choose which one they prefer. And then you will have an LLM trained with another linear layer to predict which of the 2 responses should actually get the reward 1 or 0. Like you learn with an LLM to predict what scalar you should give as a reward, like how preferable a response is as a scalar. And you would use that LLM as an extra LLM just to score your RL, your language model that you're training. I hope it was obvious because I didn't say, but the policy is the LLM itself. So this policy, this LLM, you're trying to update based on the reward that in RLHF, another LLM that you've trained from human feedback will give you. Okay. So I think for this tutorial now, we'll work with RLVF, which is the category of reward functions that are verifiable. So verifiable rewards are very reliable, are very hot right now because a lot of labs are focusing on math and coding, which are verifiable by themselves. Like you can check if a math calculation or a code snippet is running, is passing tests, and that's giving very reliable and verifiable reward signals for your LLM. So we will work with a data set called GSM-8K. It's a data set with just math problems for people in grade school. So each problem, I can actually just scroll down. Yeah, this is our RLVF. Your agent, your policy, Pi, it's your language model. It will receive prompts that you have collected from a data set beforehand. So the training data, it's really like prompts that you have gotten from, let's say, humans. And then the agent, this LLM, you just sample them with the prompt, so you will have their responses, and then you can pass them through, let's say if it's code, through a code compiler or code tests to get this gamma, whatever choice you have. Let's say 1 if it's correct, 0 otherwise, or a partial reward and so on. So the fact that it's verifiable, that means the reward is very crisp. If you think of subjective tasks, like safety, a lot of you here that I've talked to are interested in safety. Which of 2 answers are more safe or not? People will have different opinions. So maybe the LLM that will be trained on this, will be trained on these preferences, will have more noise. And this noise will propagate into your agent. With verifiable rewards, this problem is at least like partially corrected, in addition to the fact that you don't need to train another LLM. So you have double win. We focus on verifiable rewards, to be honest, mostly because adding another LLM here would have exploded the collab. So I hope you downloaded, can you download the data set as well? And you will see an example from GSMAK, which is our data set for scoring, for finding this reward function that you'll write next. So the data set is very simple. You will have this, as I said, math problems. And then the answer, you see at the end, has some rationale of how to solve that problem. And then at the end of it, you will have the final correct answer. So simply with a regex check match, you could find the final answer. You could then, like on the same question, you pass this question to the LLM, you have the LLM response, you extract the LLM answer, and you compare it with this ground truth answer from the data set. That's your verifiable reward. And then on top of that, you can put other types of reward, little rewarded parts. For instance, for the length of the response, for the format. So let's skip a little bit so you can see the reward for GSMAK. We'll have three parts in this reward function. The correctness, like the responses of the LLM and of the response in the ground truth data set in GSMAK, if they match, that has a weight of 1. The format, oops, it's like a small bonus for the LLM putting the final response into this boxed brackets. That's because, you know, the LLM could have a lot of numbers in its response. Which one of them is the correct response? You don't know. It's just easier to ask the LLM to put it in a certain format so you can extract the response of the LLM to the problem easier. And then, like again, these three components are just engineering choices. It's just to show you that you could do whatever you want to create the reward for the LLM to optimize, and then you get the juice out of it, because the LLM, if you give it a reward that is crisp and clear, it will do it. If you don't, then for sure it will be a lot of noise, and there's something that is called reward hacking, in which the LLM starts to find shortcuts in how you define the reward to solve the problem, but in an unexpected way, or in ways that you didn't want. So your exercise, if you could please look at this GSMAK reward. If you could, there's some instructions here. So you need to have the correctness part, completion contains this, and the length part. You have some helper functions, like to extract the prediction and to extract the ground truth. Use them to compute to initialize your own reward function. Who needs more time? Should we go through the solution? Okay, well, the interest of time, maybe yes. So we want to extract, the completion is just the LLM response, right? So we want to get the number prediction, response prediction from the LLM. And we also want to get the ground truth response, yeah, prediction, how should I call this? Response. And then we want to have the correctness reward to be 1 if the prediction response is the same as the ground truth response, otherwise 0. Perhaps we want to actually use the numbers match, I think, because those will be strings. So the prediction response, I'm just going to look, extract prediction. From the completion. And then the ground truth response, I think it's called extract ground truth. From the completion. And as I said, those will return strings. So you see, it's just checking for this boxed formatting that we are requesting from the LLM. Can you see? This is really like, initially we thought to give you this as an exercise, but it really doesn't make sense to have you implement a regex match. So this is really what it's doing, is trying to find in the boxed formatted thing, what is the number inside, and extract it as string or none. None, it means it hasn't found any match. Same for extract ground truth. That's very easy because already GSMAK, as I showed you, it's outputting stuff in the format that is very, you see this, I just need to check for those diez and then boom. And then I use numbers match here instead because they're 2 strings. With ground truth. And so this will be my correctness reward. I could already just keep just that. What did I do here? Sorry. Okay, so, but then I want to impose this format. Otherwise, it will be very messy, as I said, to extract what is the exact ground truth. So what I want is to have a format bonus that is just checking, like I think we set it to 0.2, but you could put more weight into it if you think it's even more important, like let's say your LLM hasn't been instruction tuned too much, then it will not know how to follow this instruction of putting into a certain format. You could put here 0.5, even 1, if you think it's as important as correctness. So it will be 0.2 if I think this boxed thing format is in my completion. And then I said, I also want a length bonus, which should be like 0.1 if, you know, the number of tokens in my completion are between min max generation, otherwise 0. So it should be 0.1 if min, hopefully it will come up here, otherwise. Where is it? Anyway, it's called min gen tokens, max gen tokens, and then this will be number of tokens in my completion that I will define in a second. Else 0. And then the number of tokens in my prediction, I think I need to use the tokenizer. So I will have like tokenizer of my completion. And I think it's searching something like, okay, Add special token false. This you don't I mean, you can check this out yourself, but like input IDs, hopefully I implemented this correctly, and then length. And then I want to add my format bonus to the reward and the length bonus. Okay. Yeah, okay, so I messed it up. Oh, yeah, that's true. Oh, thank you. Yeah, that's true. Okay, great. So this will be the reward implementation. Now, if we have the reward, we can now use it in a learning algorithm. So actually, if you could scroll up, we can try to understand PPO together. So from reinforce to PPO, we have learned reinforce before. So reinforce has one problem. It has very high variance. So because the return GT depends on an entire episode of stochastic decisions, one episode might be lucky, another one might be unlucky. There's a high variance between them, as you've seen across us, like the videos that we generate and the solutions that we generated varied quite broadly. And then the gradient estimate would also swing wildly in reinforce. So this we cannot afford with LLMs because the action space and the state space is huge. So there are a few tricks that we add to PPO to reduce that variance, to make it more stable. So first idea is to add the advantage. Advantage is just a way to say, it's just a way to define a quantity. And this quantity is trying to say, instead of, in reinforce, instead of saying, was the final score high? We don't answer that. Instead, with the advantage, what question we ask is actually, was the score better or worse than what I expected? So I will have a quantity for what I expect the return to be. And then I will have my return. I will take the difference between the two, and that's my advantage. The advantage is a way of reducing this variance in reinforce. Because if I have a positive advantage, meaning that, difference between my return and what I expected from the return, if that is a positive quantity, that means the outcome was better than I expected at this position, at this state T. And then we will reinforce those choices. So, instead of weighting by the return GT, I will weight by the advantage, which is computed in this way. And if this advantage is negative, it means like the outcome was worse than I expected. So I will discourage those, in this case, those token choices. Okay, so we already have the return, but I said we also needed the expected return. Expected return. That is yet another term for you to remember, a value function. So it's another small network. In this case, it's not a small network, it's an LLM. It's exactly the network a network that is exactly as the policy, but is a different network, so double LLM, that will just predict at every token position the expected return from that point onward. So you train this LLM, and then you use it as this quantity of getting the expected return. Just predicting, literally you train it by just predicting what would be the return from that point. You have the return, so you use a network to learn to make that prediction, okay? So you have that network, you have the actual return, take the difference, you have the advantage. This is a key refinement in PPO that is just giving lower variance. So this absorbs part of the return that is predictable. Yeah. Okay. It's a complex thing. I'm just simplifying, right? But just remember advantage value function, return minus expected return. That's your new quantity that you use to weigh your log action probabilities. The second idea in PPO is to limit how much the policy can change per update. That is called adding a clipping ratio. So PPO will compute a ratio between the new policy, the policy that it's updating, like the new LLM, log probabilities, action probabilities, sorry, the new action probabilities versus an old policy. So, yes, it's on the slide. There's a little thing, but okay. So a ratio of 1. If you look at the action probability, you have taken an action, a certain response now to this query, and you have an old policy like 10 steps ago, and your new policy. You take the action probability now, and same response, the old policy. You have the ratio of it. If the ratio is 1, that means the policy has not changed. If your ratio is far from 1, it means there is a large change. So PPO clips this ratio in the range of 1 minus epsilon to 1 plus epsilon. So it's kind of putting a bound. It's called the trust region. So the policy can only update within that bounded neighborhood of the old policy. Okay, so everything that is not within that bound will not be updated. So on top of, okay. So epsilon is just like a small margin, but basically you want to remain in this trust region of your old policy. So you don't want to have too big updates. So we had the advantage, we have the clipping. There's one last bit. I know you've been holding on. This is the last ingredient in PPO, okay? It is a KL penalty. So you add this on top of clipping, the scale penalty. So against a reference model. Okay, so you have an old policy, you have a reference model, and you have your policy that you have 3 LLMs, okay? One is the old policy that you just keep a copy of an old LLM that you have updated, few steps in the past. You have the policy, the LLM that you're updating, that you're trying to improve with RL fine-tuning. And then you have one other LLM, which is the LLM you started from. The LLM the base model, the LLM after instruction tuning. That's your base LLM that you use KL on. KL to, okay, like you don't want, let's say, that LLM, the base LLM, you don't want to diverge too much from it. You've already learned inside it some good language, some good formatting. Don't want to drift. You want to stay close. So you have KL divergence between your current policy and the reference policy, according to that formula. It is a lot, but you just remember these 3 things. You read through this, we implement this in a minute. And then GRPO is a lot simpler, and then you're done. Okay, so one more effort just to understand this, hopefully. I said we have 3 LLMs, a reference, a policy, your value model. The reward model could be, but like I said, we do verifiable rewards. You don't update all these LLMs, right? Like the reference one, you never update. You just keep it in memory so you can compare, right? So for the sake of this collab, we will actually make use of LoRa. LoRa is a way of doing low-rank transformations and stuff. You don't have to understand LoRa at this point. It's just a way of saying we will use the policy, the old policy and the reference policy as the same LLM so that we don't have to load in memory too much. I just want to do in this exercise like a small fine-tuning of a 500 million parameter model, not to exceed the GPU memories. We will use this LoRa. It's a trick. It's a trick to make things easier to train. You will not fine-tune the entire 500 million parameters. You will keep frozen everything except something in the middle, like few layers in the middle that you just train. Okay? So if we go now, please just load this, the policy with value head. That's just defining the policy. Okay? And we will implement the PPO loss a bit below. You see here it's mentioned with LoRa. LoRa is just a convenience here so that we can effectively like use the reference policy and the old policy in a shared way. Like you don't have to load 3 LLMs, as I said. Okay, please run the helper functions. The exercise to implement PPO should explain a few things. Yeah, let's say 7 minutes for this. Just try to read through it and put your hand up. I know there might be questions. Okay, so how are people doing? We don't have a lot more time. And I do want to give a high level of GRPO. Okay, let's try to think through this together. So the ratio between, how much more or less likely each token is under the current policy versus the policy that collected the data. So we are being passed this log P, log old, log ref. Well, you want here the log of the current action, log P, to have the ratio of the log of the reference, log P ref. No. No, log P old. So then this will be slightly unstable. So what you want instead is, okay, if you take the exponent of each, okay, it doesn't change anything to the objective. Okay, but then you can put the exponent e to the log P divided by e to the log P old. It's just like e to the log P minus log P old in math, okay? So, and then you want here clipped surrogate, okay? Basically you want to take the minimum between the clipped and unclipped version of the objective. So, okay, unclipped objective, okay, is like this ratio multiplied by the advantages. Okay. The clipped version is the same ratio, I think 1 minus epsilon, 1 plus epsilon. I need to look exactly the function definition. Okay, I think maybe it's just like this. Okay, I don't know where epsilon is. How did I clip epsilon? Okay. Multiply by the advantages. This is the clipped objective, sorry. And then the surrogate will be the minimum between the two. I hope I got this right. I hope. Okay, and now the KL surrogate, this is the KL, okay? So you want again to have log P minus log ref, log P ref, power of 2. And I think this is just for stability. There's a way of converting the KL to this, no, 0.2, 0.5. Okay. And then the value loss, this is all part of the expression of the PPO somewhere above, right? So the value loss, as I said, is like values, difference between what your actual values are and the returns. Values is the expected return minus your actual return to the power of 2. And then how you put it all together, you want to have like this surrogate, which has minus plus the beta KL parameter. Everything has a parameter before. Okay, times the KL surrogate plus the value coefficient times the value loss. And yes, you cannot train on tokens from the past, so you need to do a masked mean. You can check this out later. There's a ton of details to make this actually sound implementation. Yeah. Okay. Oh, and I think here I need the ratio. A ratio. Okay. Let's see. Okay. Yes. Okay, so there's a lot, especially since all the naive things that we said about the ratios and stuff. To make them more stable, you do need to apply some form of tricks, as you've seen, for stability. But if you look up any kind of implementation online, you will, or like any details about this when you actually want to implement it. Well, not just that, first of all, there's libraries for implementing this, but I think what I really want you to get from this is like, what are the components and that how unstable these things are, just to minimize that variance, to reduce that variance in the initial reinforce. You have to add all these components, but without, and you have a ton of hyperparameters already, like a surrogate, the beta KL, the value function coefficient, train the value function, and so on. It's quite sensitive, the full algorithm, to nail right. But people have, you just do a ton of parameter sweep and you find it. And also you use a bit of like your understanding of optimization and of your intuition with RL agents to actually find these parameters and do it. But it's not an easy thing, just to say. However, GRPO, which is another algorithm that has been introduced, it's just like PPO with one major change that reduces already complexity and gets rid of one of the parameters, just drops the value entirely. And then you still want to have that variance reduction. You don't want to weight your log probs. Your log prop is your backbone, right? But you want to scale them, the actions that you take, you want to scale them by some quantity that is related to reward. So you could do that with the return, but you could also just do that with something else. And to reduce the variance in the return, you have the return, and then you subtract from it some quantity that will get you just to the truth of how important that action is or not. So before in PPO, we would do that with this advantage, this expected return. But in GRPO, they just said, no, we're not going to train an expected value, an expected return. We are going to take several responses, several samples. We are going to calculate the return, for each of those responses. Like instead of taking one response to my query and getting the return just for that, like effectively just applying the reward function just on that response. Well, I'm going to take 10 responses, score all of them, take the mean of those returns, and I will use that as the quantity to subtract from the return of that sample. So I take 10 samples. I'm, let's say, on sample 1, and I want to update my policy. I'll take the average return for all those 10 samples. I have that average. I have my return for this sample 1, let's say. Return of this sample 1 minus the average return. Boom, that's the quantity I'm going to use to scale the log probability of my actions for that response. Okay, so this it will work. I think I forgot to run something. If you can run this overnight, ideally, you'll have fine-tuned an LLM. A GRPO that I just explained, you take a group, you get rid of one of those networks. It's not as stable as PPO, but it's very hard to get wrong. It's harder to get wrong than PPO. It's easier to get right, let's say. Let's put it like this. And really, like, as I said, just to implement it quickly, you have the group mean, the group standard deviation, very easy implementation, actually. You are which I just absolutely cannot find. Okay, so you want to have the rewards mean. The standard deviation is the reward standard deviation, as I said. Okay, and then your advantages, which is the new baseline, you want to have like the reward, the advantages is really like the thing that you're going to use to weight your log probabilities of the actions. You have the rewards minus the group mean. Okay. And here you'll have the group standard deviation divided by the group STD, plus some epsilon, so you don't collapse if in case everything is 0. So this, okay, this would mean that if you have a query and you sample 10 responses, on all of them get reward 1, how useful a signal is that? Like, how useful is that sample? How useful is that prompt? Well, the mean will be the same, like the mean will be, the standard deviation will be 0, okay? So that sample is not good, you remove it. Because you have no variance in your responses, there's nothing to learn, like there will be no update on it. So the group, this group reward can also be a signal to do rejection sampling if you are familiar. So this is simpler. And then for you as homework, I think it would be great if you could look into DPO, which is even more simpler in the sense of like it's saying, forget about a reward function. Just use already the preference data itself to update the weights of the policy. Okay, I know this was a lot. We're a bit over time. We also started a bit over time, but I hope some concepts in RL have become slightly clearer. If this is the first time you're doing RL, I hope like some words you'll remember. And if you are very advanced in RL, I hope you were not too bored. And if you have more specific RL questions, I'm here the full week and I'm happy to talk about RL, LLMs, anything. Thank you so much. I wished I had like an LLM joke to finish this, but I haven't generated it. So thanks a lot. I hope you enjoyed this and yeah.